Imagine waking up one day to discover that everything, Earth, the stars, the farthest galaxies, isn't floating in empty space, but trapped inside the most mysterious object in the universe, a black hole. It sounds absurd, even impossible. But what if it's not? Black holes are supposed to be the final destination for matter and energy. But some physicists now wonder if they might also be beginnings. What lies beyond the event horizon might not be a dead end, but a doorway. And if that's true, then a bold question emerges. Could our universe be the interior of a black hole in some larger reality? It's a radical idea, and it just might explain where we came from, what reality is made of, and how everything could end. The edge of reality. What the event horizon truly means. At the center of a black hole, something happens that breaks the rules. But long before you reach that central point, there's a boundary. It's called the event horizon. Most people have heard the name. It's the surface that marks the point of no return. Once something crosses it, not even light can escape. But what does that really mean? The event horizon isn't a wall. You wouldn't bump into it like a spaceship hitting a force field. If you were falling into a large black hole, you might not even notice anything when you pass through it. There are no strange lights, no sudden changes in pressure or temperature. You wouldn't feel like you had crossed some limit. But from that point on, everything you knew about space and time would begin to slip away. What makes the event horizon so strange isn't just what happens after you cross it. It's what it means for the rest of the universe. Think of it this way. The event horizon doesn't just hide what's inside a black hole. It actually makes it impossible for information to get out. Anything that goes in, light, particles, energy, even the record of an object's history, is cut off from the outside world. It's not just out of reach, it's erased from our universe in terms of what we can observe or know. The black hole doesn't send back clues. Once something crosses the event horizon, it's gone. This is where things start to feel less like physics and more like philosophy, because the laws of physics are built around the idea that information isn't lost. Even when something is destroyed, say when a log burns in a fire, the information about the atoms and energy involved still exists. It just changes form. But black holes, and especially their event horizons, seem to break that rule. From the outside, all we can see is the gravity of the black hole pulling in more mass. We don't get to know what fell in, or how. The details are locked away behind the event horizon. This has puzzled physicists for decades. The event horizon also bends the way time works. From the outside, it looks like anything falling into the black hole slows down as it approaches the edge. In fact, it appears to freeze right at the surface. A spaceship falling into a black hole would seem to hover at the event horizon forever, gradually fading into red light, then vanishing from view. But from the point of view of the people inside the ship, time moves normally. They cross the horizon and continue falling toward the center, unaware that from the outside, they have stopped moving at all. Two very different experiences of time, both happening at once. This split between inside and outside creates a deep mystery. If you're on the outside of a black hole, there's no way to get any information about what's happening on the other side of the event horizon. The rules of reality as you know them, space, time, cause and effect, simply don't apply there in the same way. From this perspective, the event horizon is the edge of reality. Now imagine this boundary from the point of view of the universe. The laws of physics work by allowing you to predict the future from the present. If you know the position and motion of every particle in a system, you can calculate what will happen next. But with a black hole, you lose part of the system. Anything behind the event horizon is cut out of the equations. This means that the rest of the universe is affected by something it can't ever see or measure. If there are regions of the universe that are forever hidden, how much can we ever really know? Is physics about describing what exists, or only what can be observed? The event horizon forces us to confront that difference. It shows us that even the most basic ideas, like space and time, depend on where you are and how you're moving. That means there may be no single, complete story of the universe. There may only be pieces, stitched together by the limited view of each observer. Some physicists think that everything that happens inside a black hole might be encoded on its surface, on the event horizon itself. This idea comes from a theory called the holographic principle. It suggests that the event horizon may hold all the information about what's inside the black hole, like a two-dimensional code that projects a three-dimensional reality. If true, it would mean that the event horizon isn't just a boundary, it's a kind of cosmic hard drive, storing everything that ever crossed into the black hole. Not as objects, but as patterns of information. It's a radical idea, and one that's still being explored, but it could solve some of the biggest puzzles in physics, including the question of whether information is truly lost. No one has ever seen an event horizon directly, but we've seen signs of their effects, like the shadow of the black hole imaged by the Event Horizon Telescope in 2019. That shadow wasn't the event horizon itself, but it showed us where it had to be. It was the absence of light, carved out by gravity. A kind of ghost, drawn not by what's there, but by what's no longer allowed to leave. Like the horizon on Earth, the event horizon of a black hole marks the edge of what we can see, but not necessarily the edge of what exists. Beyond it may lie something we'll never reach, never measure, never understand. The hidden geometry beneath space-time. According to Einstein's theory of general relativity, gravity isn't really a force in the usual sense. Instead, it's the way mass and energy curve the fabric of space-time itself. The more mass you pack into a small space, the more extreme the curve becomes. And in the case of a black hole, the curve becomes so steep that space folds in on itself and time slows down to a stop at the edge. Around Earth, gravity bends light only a tiny bit, just enough to make GPS satellites adjust their clocks. But around a black hole, this bending becomes so intense that light can orbit it in perfect circles, caught in a trap made entirely of warped geometry. If you were to shine a flashlight sideways at just the right distance from a black hole, the beam could circle the hole over and over again before finally being swallowed. That distance is called the photon sphere, and it marks a kind of unstable loop where light itself becomes a prisoner of curved space. Deeper in, near the event horizon, even stranger things happen. Space-time is no longer just curved. It starts to tilt. For something falling in, the direction of time and the direction of space begin to swap places. Moving forward in time becomes the same as moving inward toward the center. That's why nothing can turn around and escape. It would be like trying to run backward through time. Once you cross the event horizon, the geometry forces you in one direction only, down. The equations of general relativity allow for all kinds of strange shapes hidden inside a black hole, shapes that might not make sense in the world outside, but are mathematically possible within such extreme gravity. One possibility is something called a closed time-like curve. In simple terms, this is a path through space-time that loops back on itself. If you followed it, you could end up where, or even when, you started. These loops appear in some solutions to Einstein's equations, especially in the kinds of warped spacetimes found inside rotating black holes. The idea comes from a type of black hole known as the Kerr black hole. Unlike a simple, non-spinning black hole, a Kerr black hole has angular momentum. It spins like a giant cosmic whirlpool. This spinning motion doesn't just twist the matter that falls into it, it also twists the space-time around it. The faster it spins, the more intense the twisting becomes. According to the math, near the core of a spinning black hole, this twist becomes so strong that you might be able to follow a path through time that curves back to your own past. These paths don't require a time machine. They form naturally in the strange geometry inside the black hole, like loops hidden in the folds of a scarf. If such loops exist, could something inside the black hole travel through time? Could events inside loop endlessly, repeating over and over? Could a particle, or even information, escape this cycle? Physicists aren't sure whether closed time-like curves are real or just mathematical quirks. There may be unknown laws that prevent them from forming, Or maybe the universe simply doesn't last long enough for them to matter. But the fact that they appear at all shows just how strange and flexible space-time can become when pushed to its limits. Another idea that comes from this hidden geometry is the concept of folded space. Inside a black hole, space can be bent in extreme and surprising ways. In some theories, the core of a black hole isn't a single point, but a tunnel, a shortcut through space and time, known as a wormhole. Wormholes are solutions to Einstein's equations that look like two regions of space connected by a narrow throat. Theoretically, something could pass through a wormhole and come out the other side in a completely different place, or even a different time. These wormholes aren't stable in real life, at least not without exotic matter to hold them open. But the geometry still exists in the math. In certain models of spinning or charged black holes, the inner core doesn't collapse to a point, but opens into a bridge leading somewhere else. Some versions of this geometry would even allow you to avoid the singularity entirely, to pass through the black hole instead of being destroyed by it. The idea of a hidden path or folded bridge under the surface of a black hole is deeply speculative. We don't have proof it's possible, but if space-time can be bent into loops and tunnels, then perhaps black holes are not just endpoints, they may also be doors. There are other signs that geometry behaves strangely near black holes. One of them comes from what's known as frame dragging. This is the effect caused by a spinning mass twisting space around it. Near a fast-spinning black hole, this dragging becomes so strong that it forces everything nearby to rotate along with it. Even if you tried to hover in place, you'd still be carried around. Space itself is turning. This twisting geometry means that directions break down. Up and down stop having the same meaning. Time begins to flow in strange directions. And as you get closer to the center, every rule you thought applied begins to melt away. The geometry under the surface no longer follows the map of ordinary reality. The deeper you go, the less the normal rules apply. The coordinates we use to describe space stop making sense. The distance between points becomes hard to define. Time becomes tangled with space, and motion becomes trapped in directions that can't be undone. They are the logical consequences of Einstein's equations, stretched to their extremes. In the world of general relativity, geometry is the stage on which the universe plays out its story. And near a black hole, that stage becomes a funhouse of curves, loops, and spirals, a place where straight lines don't stay straight, and time itself may run in circles. The event horizon may be the limit of what we can observe, but it's not the limit of what geometry can do. Beneath it lies a hidden world, a world that may be filled with folded space, twisted time, and a place where the very structure of the universe turns in on itself. The singularity, a crisis in our understanding. The word singularity conjures up images of a tiny dot at the very center of a black hole, a place where everything is crushed down to nothing, a point with no size but infinite density. Gravity becomes so strong there that space and time no longer make sense. This picture is dramatic, but it might also be wrong. The truth is, the singularity may not be a real place at all. It might just be a sign that our math, and even our best physical theories, stop working. In the world of physics, whenever something becomes infinite, it usually means something is broken. Infinity isn't a number you can reach. It's the warning light on the dashboard. It tells us that we've pushed a theory beyond its limits. In general relativity, the singularity appears as a place where space-time curves too sharply to be described. Gravity keeps increasing until it's off the scale. The formulas that describe motion and energy and light can't return answers anymore. Instead of giving us numbers, they give us nonsense. This happens right at the center of the black hole, the place where all the matter that fell in is thought to collapse. But general relativity doesn't include everything. It's a theory of gravity, of large-scale motion, of planets and stars and galaxies. It doesn't include the rules that govern very small things, like atoms or particles. those are handled by quantum mechanics. And right now, the two theories don't work well together. This becomes a problem in places like a black hole's center, where both gravity and quantum effects are extremely strong. We can't just ignore one or the other, but we also don't yet have a single theory that combines both. So when we talk about a singularity, we're really talking about a place where our current understanding breaks down. It's not a dot in space, it's a question mark. What really happens to matter and energy that fall into a black hole? Do they shrink forever? Do they get erased? Do they bounce into another universe? Our theories don't have a clear answer, not because there's no answer, but because we don't yet have the tools to find it. Some physicists believe the singularity will disappear once we have a complete theory of quantum gravity, a theory that blends the bending of space with the uncertainty of particles. In this future theory, gravity wouldn't be a smooth curve like in Einstein's model. It might come in tiny chunks, like the pixels of a screen. Space and time themselves might have a smallest possible unit. And if that's true, then maybe the singularity never really forms. Maybe what looks like a point of infinite collapse is actually a kind of quantum structure. There are already hints that this might be the case. Some versions of quantum gravity, like loop quantum gravity, suggest that space is made of tiny loops. In that framework, when matter collapses under gravity, it doesn't form a true singularity. Instead, the loops create pressure that resists further collapse. Instead of a bottomless pit, you get a kind of bounce. Other theories, like string theory, take a different route. They imagine that all matter is made of vibrating strings far smaller than atoms. In these models, extreme conditions like those near a black hole's center change the nature of the strings. New types of particles or dimensions might appear. The singularity becomes not a place where laws break, but a place where new laws take over. Even though we don't yet know which of these ideas, if any, are correct, they all share something important. They treat the singularity not as a final truth, but as a signpost. It points to the edge of our knowledge. It's where the map ends. There are other clues that the singularity isn't a complete story. For example, in the early days of the universe, just after the Big Bang, the equations also predict a singularity. Everything in the cosmos compressed into one point. But most scientists now believe that this early state wasn't a true singularity either. Instead, it was an extremely dense, hot, and chaotic moment that we still don't fully understand. A moment when quantum effects matter deeply. So maybe black hole singularities are like that too. Not real objects, but signs of something we don't yet grasp. One of the hardest parts of studying black holes is that we can't test what's happening near the center. All we have are theories, clues from math, and patterns we can observe from the outside. But when it comes to the singularity, we're blind. This makes the problem even more urgent. If our models give us infinities, it means we need new ones. Physics isn't just about describing what we see. It's about finding simple rules that explain why things behave the way they do. There's also another problem that grows from the idea of a singularity. If it's truly a place where time ends, what happens to the idea of cause and effect? What happens to the idea of the future? Does time stop, or does it wrap around into something else? Our usual ways of thinking don't apply. A singularity isn't just a problem in space, it's a problem in logic. It asks whether the universe always makes sense, or whether there are corners where reason itself fails. Like explorers sailing toward an unknown island, many scientists hope to find new ideas, new math, and new rules waiting at the edge. Already we're starting to make progress. New observations of black holes, from gravitational waves to shadow images, are giving us better data. And powerful telescopes, combined with better theories, may one day help us piece together what happens at the heart of these mysteries. Are all black holes the same on the inside? From a distance, black holes all seem to act the same, but the truth is more complicated. Just like stars come in many sizes and types, black holes may have their own internal differences. On the outside, they might look alike, a dark sphere surrounded by swirling gas. But on the inside, they could be telling very different stories. The most obvious difference between black holes is their size. Some are only a few times heavier than the Sun. Others are millions or even billions of times heavier. These are called supermassive black holes, and they live at the centers of galaxies. Then there are tiny black holes, ones that might have formed in the early universe, long before stars or planets. These are known as primordial black holes. Each of these types might warp space and time in its own unique way. Stellar mass black holes are the kind formed when a star dies in a supernova explosion. These black holes typically weigh between 5 and 50 times the mass of the Sun. Their event horizons are only a few kilometers wide. The gravity there is intense. If you were to fall towards such a black hole, you'd feel the pull on your feet much stronger than on your head. The difference would stretch you out. This effect is known as spaghettification. In small black holes, it happens quickly, long before you reach the center. Now imagine a much bigger black hole, a supermassive one, like the kind found in the center of the Milky Way. Its event horizon can be millions of kilometers wide, big enough to contain orbits the size of our solar system. And yet, the pull of gravity near the horizon is surprisingly gentle. If you were to fall in, you might not even notice anything strange at first. The difference in pull between your head and feet would be tiny. You wouldn't feel yourself stretching. You'd simply float across the horizon without pain or pressure. It's only much later, far closer to the center, that gravity would ramp up. This difference in scale hints at something important. The interior of a supermassive black hole may be structured very differently from a smaller one. It may give matter more time before it breaks down. It may allow for more complex interactions inside. In theory, it could even allow enough space and time for entirely new kinds of physics to emerge deep within. Some physicists believe that supermassive black holes might not just be bigger, but fundamentally different. Their size could allow for stable zones inside, places where particles could survive longer, or where quantum effects might change the way matter behaves. Some extreme models even suggest that large black holes could contain inner surfaces, or regions with different geometries, where the rules of space and time break and then reform in new ways. Then there's the idea of primordial black holes, tiny ancient objects that may have formed just after the Big Bang. These wouldn't come from dying stars. They'd come from regions of high density in the early universe, where matter collapsed before galaxies even had time to form. Some might be as small as an asteroid. Others could be heavier than the Moon. In theory, these black holes could still exist today, hidden across the cosmos. Some scientists have even wondered if they could make up dark matter. If primordial black holes are real, their insides could be unlike anything else in the universe. Since they didn't come from stars, they wouldn't carry the same collapse history. Their cores might never have gone through fusion or supernova stages. Instead, their formation would be pure geometry, space folding in on itself without the usual mess of heat and light. Because they'd be so small, quantum effects would dominate their insides. Hawking radiation, the slow leak of particles that causes black holes to shrink, would be stronger. If they were small enough, some might already have evaporated completely. If they still exist, their interiors might be shaped more by quantum fluctuations than by classical gravity. Instead of a smooth singularity, they might contain bouncing fields, loops of energy, or strange forms of matter. Another interesting question is whether black holes with electric charge or spin have different internal setups. A non-spinning uncharged black hole is the simplest kind, called a Schwarzschild black hole. But most real black holes aren't that simple. They rotate, and many may carry some charge, at least for a short time. A spinning or Kerr black hole has a more complex structure inside. Instead of a single point-like singularity, it may contain a ring, a loop where space becomes undefined. In some versions of the math, this ring singularity could lead to other regions of space, maybe even to other universes. But before that happens, something else might get in the way: instability. The inner structure of rotating black holes may be unstable. As matter falls in and spins build up, the geometry might twist so much that the interior becomes chaotic. Tiny changes could ripple into larger effects, breaking apart any smooth structure inside. This could mean that real rotating black holes don't have peaceful tunnel-like interiors, but instead, wild storms of curved space, where no paths are stable and no predictions hold. Charged black holes, known as Reissner-Nordstrom black holes, have their own quirks. The math suggests that they could have not one, but two horizons, an outer one and an inner one. Between them lies a region where time and space switch roles in strange ways. In theory, this setup allows for some very odd possibilities, like objects moving from one horizon to the other without hitting the singularity right away. But again, this is mostly mathematical. In the real world, charge may not last long. The black hole could neutralize quickly, and the inner structures might collapse before they can form. These are just a few examples. And they all point to one thing. The inside of a black hole might not be a one-size-fits-all story. It could depend on how the black hole formed, how big it is, whether it spins, what kind of matter fell in, and how fast. Two black holes with the same mass might have very different histories and very different interiors. So what happens when black holes collide and merge? Does the interior structure of each one get preserved? Or is everything erased and replaced with something new? We know from gravitational wave detectors like LIGO that black holes do merge. These ripples in space-time show us how they orbit, crash, and settle into one. But what happens inside during that process is still a mystery. Some physicists wonder whether the inner structures of black holes might carry information that could survive such collisions. Others think that whatever was inside gets scrambled or lost. If there are differences inside black holes, maybe those differences could leave subtle marks on the gravitational waves they emit. Future detectors might be able to find those patterns. A universe inside a black hole. Serious physics or just metaphor? There's a strange idea in physics that goes like this. If you take all the mass in the observable universe, every galaxy, star, planet, atom and particle, and ask how strong the gravity is, you can actually calculate something called the Schwarzschild radius. That's the radius where, if you packed all the mass into a sphere, it would become a black hole. And here's the twist. If you do the numbers, the radius you get is about the same size as the universe itself. Which raises a wild question. Is the universe already inside a black hole? If the universe's total mass fits within its own Schwarzschild radius, then from a certain point of view, the universe meets the basic condition for being a black hole. At first, this sounds like a trick, just a coincidence of numbers. After all, the universe isn't collapsing, it's expanding. We don't feel a crushing pull, but the math goes deeper. Black holes aren't defined by collapse alone. They're defined by the shape of space-time they produce. If the shape is similar, even if it's expanding, the question becomes more serious. Some physicists have explored this idea by comparing the structure of a black hole's interior with models of our expanding universe. Surprisingly, in some cases, the two look very similar. The way time flows, the way distances stretch, the way light behaves, these can all match depending on the model. Inside a black hole, beyond the event horizon, time and space switch roles. What used to be a direction in space becomes a direction in time. In an expanding universe, something similar happens. Space stretches in all directions, and the past boundary, the Big Bang, acts almost like a kind of horizon. You can't see past it. Information from before it can't reach us. It's a limit, just like the edge of a black hole. There are also more technical reasons to think about the universe this way. In a paper published in the 1960s, physicist Andrei Sakharov proposed that the Big Bang might actually be the other side of a black hole, not a collapse, but a bounce. Others followed up with more ideas. Could a black hole's singularity actually lead to the birth of a new universe? Instead of ending, does the matter and energy falling into a black hole go somewhere else? Not into nothingness, but into a new space, a kind of cosmic womb. Some solutions to Einstein's equations allow for black holes to connect to other regions of space-time, possibly even creating baby universes on the other side. The black hole's interior becomes the beginning of something else. From the outside, the black hole just looks like a simple object, but inside, it might be the birth of an entire cosmos. This turns the picture of black holes upside down. Instead of being ends, they become beginnings. And if that's possible, then maybe our universe began the same way. Not from nothing, but from the inside of a black hole in some other, larger universe. There's something elegant about this picture. It could explain why the universe has the energy it does. Black holes come with very specific balances of energy, pressure, and temperature. Our universe has those things too, in just the right amounts to allow stars, galaxies, and life to form. If the universe were the inside of a black hole, maybe those conditions aren't random. Maybe they follow from deeper laws about how black holes work in a bigger cosmic system. Does saying the universe is inside a black hole mean anything physical? Or is it just a way of looking at the equations? There's no edge we can cross, no surface we can point to and say, here is the event horizon. We're not trapped. Light can move. And we don't see anything on the outside. No parent universe, no giant observer watching us fall in. Some physicists say this idea should be treated carefully. Just because equations look similar doesn't mean the situations are the same. In a black hole, the event horizon is a place you can point to from the outside. In our universe, there's no such vantage point. There's no outside observer looking down on the universe's edge. From inside, we experience the expansion, the flow of time, and the shape of space, but we have no way to step back and see it all at once. Others say that's exactly the point. Maybe there is no outside. Maybe the universe is like a black hole, not because it sits inside one, but because black holes and universes follow the same deeper pattern. Maybe the laws that shape a black hole also shape reality as a whole. Every black hole, when it forms, might create a new universe on the inside. Our universe might be one of many, born from the collapse of some massive star in another realm. And every black hole in our universe might be a seed for another cosmos, hidden beyond the event horizon. This would create a kind of cosmic tree, a branching network of universes, each growing from the collapse of matter in another. This idea is called cosmological natural selection, and it's been explored by scientists like Lee Smolin. In this view, black holes are the engines of creation, making new universes with each collapse. What once seemed like the dead end of physics, a place where everything breaks, is now being reimagined as a doorway. There's still no direct evidence that our universe is inside a black hole. It's an idea born from theory, not observation. But the fact that serious physicists are asking these questions shows how strange and flexible reality might be. One day, we might understand the early moments of the universe better. We might learn more about singularities, quantum gravity, and the shape of space. And when we do, we might discover that black holes and universes aren't separate ideas. They're different sides of the same coin, connected by geometry, energy, and the strange logic of space-time. Does the cosmic horizon act like an event horizon? No matter how powerful our telescopes become, there's a hard limit to how far we can see. Not because of dust or darkness, but because of something more fundamental, the speed of light and the way the universe expands. This limit is called the cosmic horizon. Beyond it, space exists, but the light from those regions hasn't had enough time to reach us yet. It's not just that it's too far, it's that, by the rules of physics, it's impossible for us to ever see what's on the other side. And that's where things start sounding familiar, because in many ways, this cosmic horizon behaves a lot like the event horizon of a black hole. A black hole's event horizon is the point of no return. From the outside, it's a one-way surface. Information goes in, but not out. You can't see past it, and no matter what you do, you can't escape it. Now think about our cosmic horizon. We can look out across billions of light years, seeing galaxies as they were in the distant past. But only up to a point. Beyond that, galaxies are moving away from us so quickly, because of the expansion of the universe, that their light will never reach us. It's not because they're moving through space fast. It's because space itself is stretching faster than light can keep up. It's like trying to run on a treadmill that gets longer every step you take. Eventually, you can't make progress anymore, and that creates a kind of horizon. Are these two horizons fundamentally the same thing, or are they just similar in appearance? To answer that, it helps to look at how each horizon works. A black hole's event horizon is local. It surrounds a single object with a very strong gravitational pull. It's shaped by the black hole's mass and spin. From the outside, the event horizon stays the same, a fixed, constant surface. The cosmic horizon, on the other hand, isn't about a single object. It's about the entire universe. It changes over time. In the early universe, the horizon was much smaller because there had been less time for light to travel. As the universe aged, the horizon grew, but now parts of the cosmos are beginning to slip away again. Galaxies we can see today will eventually move out of view. Their light won't reach us anymore. They will disappear, not because they've gone anywhere, but because the horizon has caught up with them. Still, the two kinds of horizons share some surprising traits. Both horizons hide information and both have temperatures. That sounds strange, but in quantum physics, horizons aren't just empty boundaries. They're active. Black holes give off Hawking radiation due to quantum effects near the event horizon. Similarly, the cosmic horizon has its own temperature tied to the expansion rate of the universe. It's much colder than the coldest vacuum we can imagine, but it's not zero. That means space itself, even empty space far from any star, has a kind of thermal glow linked to its horizon. Is the cosmic horizon just a limit to our knowledge? Or is it something real? A kind of wall in space-time? And if it is real, does that mean we're trapped inside something, just like anything inside a black hole? Some physicists have asked if there's a kind of event horizon for observers like us, not just in a black hole, but in the universe itself. This idea is sometimes called a de Sitter horizon, after a solution to Einstein's equations where space expands forever. In that solution, every observer has their own personal horizon, a limit to what they can see, shaped by their position, and the way the universe expands around them. These horizons behave in many of the same ways as a black hole's event horizon. They block information, they carry entropy, they even radiate, at least in theory. If that's true, then maybe the universe is more like a black hole than we thought, in the sense of having boundaries built into the geometry of space and time. We might not be in a black hole, but we're still surrounded by a horizon, not a surface of matter, but a surface of limits, a place where our knowledge, our signals, and our ability to interact with the wider universe ends. In both cases, black hole and universe, the horizon isn't fixed in place. It depends on the observer. In a black hole, someone falling in doesn't feel the horizon. To them, there's no sharp boundary. But to someone watching from the outside, the horizon is real and permanent. In the universe, the same thing happens. Depending on your location and motion, your cosmic horizon might be slightly different. You might see a different patch of the sky or have a different limit to what you can observe. That means horizons aren't absolute. They're part of the way observers interact with the universe. They're shaped by motion, perspective, and the flow of time. Reality itself might be different for different observers, not just in how it appears, but in what exists for them. This idea, called horizon complementarity, suggests that no single observer can see all of reality. Everyone gets a slice. In a black hole, the person falling in and the person staying outside experience different versions of the story, and both are valid. In the universe, we each have a cosmic horizon shaped by our past, our motion, and our position in space. Beyond that, we can't reach. So in a sense, each of us lives inside a kind of personal bubble which defines what is real for us. There might be places we can never see, events we can never know about, and galaxies we will never reach. Not because we aren't clever enough, but because of the very rules that shape the universe. In that sense, the cosmic horizon is like an event horizon, a reminder that we live inside a universe with edges, not walls, but limits. And just like the edge of a black hole, those limits might tell us something important about the deeper shape of reality. The holographic universe, a shadow projected from a higher dimensional surface. In the 1970s, physicist Jacob Bekenstein made a surprising suggestion. Maybe black holes actually do store information, not inside, but on their surface. The amount of information a black hole could hold seemed to be related not to its volume, but to the area of its event horizon, the invisible boundary that surrounds it. This idea suggested that in some way the surface of a black hole contains all the information about what has fallen into it. Stephen Hawking later added another twist. He showed that black holes aren't completely black. They can give off radiation due to quantum effects near the horizon. Over time, they shrink and evaporate. But if they're losing mass and the information is stored on the surface, what happens to that information when the black hole disappears? Physicists debated this question for decades. Some thought information was destroyed, which breaks the rules of quantum mechanics. Others thought it might be preserved in the Hawking radiation itself, scrambled in some mysterious way. But a different idea began to take hold, one that turned the entire problem inside out. What if the information about everything inside the black hole isn't really inside at all, but is somehow encoded on the surface? Not just stored there, but truly represented there. What if the three-dimensional contents of a black hole are a kind of hologram, a projection from a two-dimensional surface? A hologram, in the everyday sense, is a flat image that looks three-dimensional. If you've seen one, you know the trick. The image is stored on a two-dimensional surface, but the way light interacts with it creates the illusion of depth. But in the holographic principle, it's not just an illusion. The idea is that a full 3D reality, including space, time, gravity, and everything we experience, could actually be described by information that lives on a 2D surface. Imagine a cube of space. The cube holds information, stars, planets, atoms, and that information is spread throughout the volume. But the holographic principle suggests the true amount of information inside that cube might be limited by the surface area of the cube, not the volume. Just like with a black hole. The idea got a major boost in 1997 when theoretical physicist Juan Maldacena found a way to connect two very different theories. One that described gravity in a five-dimensional space, a kind of bulk space, and one that described quantum fields without gravity on a four-dimensional boundary of that space. These two theories, though completely different in how they were written, turned out to be mathematically equivalent. Everything that happened in the five-dimensional world with gravity had a counterpart in the four-dimensional world without gravity. It was like having two languages that told the same story. This became known as the ADS-CFT correspondence, short for anti-de Sitter conformal field theory. And while it applies to a special kind of universe, not quite like ours, it showed that a holographic description of reality was possible. A universe with gravity could be fully described by a theory without gravity living on a lower dimensional surface. Space and time in the bulk could emerge from quantum information on the boundary. It was a turning point. If such a duality was possible in this artificial setting, could something similar apply to our universe? In our world, space is expanding, and we don't live in an anti-de Sitter space. But the idea opened up new ways to think about gravity, quantum mechanics, and information. More and more physicists began to ask, what if our entire universe is a kind of hologram? If that's true, then the three-dimensional world we experience, the movement of planets, the flow of time, the shape of galaxies, might be a projection. The true data of the universe could live on a distant boundary, perhaps far beyond our cosmic horizon. everything around us would behave as if it were fully 3D. But at a deeper level, the rules might come from a flat sheet of information on a two-dimensional surface. This sounds outrageous, but there are reasons to take it seriously. For one, the holographic principle solves the information problem for black holes. If the information is on the surface, it's not lost. It also provides a way to unite quantum mechanics and gravity, two theories that normally don't get along. In quantum theory, information is preserved. In gravity, space can stretch, bend, or even tear. But if gravity is an emergent effect, something that arises from quantum information on a lower dimensional surface, then maybe we don't need to quantize space itself. Maybe space is a side effect, not a starting point. There's another hint too. When physicists try to calculate the amount of entropy, the measure of disorder or hidden information, in a region of space, they keep finding that the maximum possible entropy is linked to the area of the region's boundary, not its volume. This keeps happening in black holes, in quantum field theories, even in simple thought experiments. It seems like nature is trying to tell us something. Information lives on surfaces. Still, many questions remain. If the universe is a hologram, where is the screen? What is the boundary? Is it the cosmic horizon? Is it a mathematical surface at infinity? Or is it something else entirely, a place we can't even point to in ordinary space? And what does it mean for reality? If the universe is a projection, does that change what it means to be here now? Are we shadows cast by information? Is time itself just part of the projection? No one knows for sure. For now, the holographic principle remains a powerful idea, not proven, but deeply connected to the best theories we have. It offers a new way to think about the universe, not as a place made of matter and energy, but as a system of encoded information playing out across a cosmic surface we can't see. The world around us may be real, but it may also be a reflection of something deeper, a story written on a far-off boundary, playing out like a hologram in the dark. Could the Big Bang have been a white hole? The Big Bang is thought of as the beginning of everything. Space, time, matter, and energy all bursting outward from a single point. But what if the Big Bang wasn't the start of everything, but the result of something else? Some physicists think it's possible the Big Bang wasn't a beginning at all, but an event triggered by a very unusual object, something called a white hole. A white hole is a strange and still theoretical idea. It's supposed to be the opposite of a black hole. Where black holes pull things in and never let them out, a white hole does the reverse. Nothing can enter, and everything inside gets pushed outward. If you imagine time running backward in a black hole, it would behave like a white hole. Instead of collapsing inward, everything would be forced to explode outward. Mathematically, if you flip the direction of time in the equations for a black hole, you get something that behaves like a white hole. So far, we've never seen one. Black holes, by contrast, are everywhere. We've detected them through the stars that orbit around them, the X-rays they emit when feeding, and even the gravitational waves they release when they crash into each other. White holes, on the other hand, remain entirely hypothetical. But the math behind them works, at least in theory. The Big Bang already looks like an explosion, a sudden expansion of hot, dense matter into space. So why not just say it was a white hole and be done with it? But the connection goes deeper than that. A white hole doesn't just explode randomly. It's often seen as the end result of something that's been trapped inside a black hole. So if the Big Bang was the explosion of a white hole, then maybe the matter and energy we see in our universe today came from something that fell into a black hole elsewhere. Maybe our universe is the interior of a white hole that formed when a black hole collapsed in some larger universe. The matter inside a black hole in one universe could be squeezed so tightly that it bursts out the other side, creating an entirely new region of space-time. Some ideas in loop quantum gravity suggest that black holes don't end in singularities. All the matter falling in gets compressed, but instead of being crushed to a point, it rebounds. If that happens, then the other side of a black hole might look like a white hole, with all the trapped matter bursting out again into a new region of space. Every black hole could become the seed of a new universe, and from the inside, the new universe might never know it came from somewhere else. Its inhabitants would see their universe expanding outward, just like we do. They would trace their cosmic history back to a hot, dense beginning, what we call the Big Bang. But they'd have no clue that the bang came from a collapse in another universe. This answers a few big questions. One of them is about the origin of time. If time begins at the Big Bang, where did it come from? What set it all in motion? If our universe is born from a black hole in another universe, then time was already ticking. The Big Bang wouldn't be the true origin of time, but a continuation of a timeline that began elsewhere. Another question is about black hole interiors. If nothing ever escapes a black hole, where does all the stuff go? Is it stuck forever? Does it disappear? Or does it find a way out? The white hole idea offers an escape hatch. Instead of being destroyed, the matter gets recycled. It re-emerges in a new form, in a new cosmos. Of course, this idea is full of challenges. First, we have no direct evidence that white holes exist. None have been observed, and their behavior might make them impossible to see. Second, the conditions needed to create a white hole might be extremely rare, or impossible in our universe. And third, we don't know if the laws of physics would allow such a connection between black holes and new universes. Still, there are some hints that push this idea forward. When we look at the universe today, we see that it's remarkably smooth and even. The temperature of the cosmic microwave background is nearly the same in every direction. This is surprising because those regions of space were never in contact with each other. They shouldn't be able to know how to match their temperatures. This is known as the horizon problem. Inflation, a theory that says the early universe expanded faster than the speed of light, helps solve that. But so does the white hole idea. If the matter in our universe came from a black hole, then it could have been packed tightly together before the bounce, allowing temperatures to even out before expanding. The white hole model gives a different way to explain the same observations. There's also the idea of cosmic censorship, a concept in general relativity that says singularities must always be hidden behind event horizons. If true, it means that we should never see the center of a black hole. But what if the Big Bang was a singularity that we can see? That would break the rule, unless it wasn't a true singularity. If it was a white hole, then the bang might be the visible side of something much deeper. Some versions of this idea also link back to the holographic principle. If space-time is emergent, if it arises from quantum information on a boundary, then maybe the process of forming a new universe is really a shift in how information is encoded. A black hole in one system becomes a white hole in another through a change in perspective or description. Other researchers have tried to model white holes more directly. Some think they could form naturally as black holes age and evaporate. After losing most of their mass, the black hole might flip into a white hole state, spitting out everything it once swallowed. This would happen near the end of the black hole's life, after billions or trillions of years. But in that case, it wouldn't create a new universe, just spew matter back into ours. Still, the idea remains. Maybe our Big Bang was a one-time white hole event, not the end of a black hole in our universe, but a black hole from somewhere else entirely. When universes collapse, do black holes seed new Big Bangs? If black holes can form when stars collapse, then what happens when something much bigger collapses, like an entire universe? Could that too give birth to something new? A collapsing universe might form something like a black hole in a higher dimensional space, and what's on the other side could be a brand new universe, expanding outward, unaware of where it came from. In our current universe, space is expanding, but it wasn't always that way, and it might not stay that way forever. In some models of the universe, expansion doesn't go on forever. Eventually, gravity could slow it down, stop it, and then reverse it. Everything would begin falling back together. Galaxies would draw closer, stars would burn out, matter would clump, space would shrink. Time would tick faster and faster as everything rushed toward a final collapse, a kind of big crunch. This big crunch would be the opposite of the Big Bang. Instead of a sudden burst of growth, it would be a slow but unstoppable collapse. The universe would shrink to a point, and the density of matter and energy would increase until the laws of physics could no longer describe what's happening. Just like the center of a black hole, this point would become a singularity. If the death of a massive star can lead to the birth of a black hole, maybe the death of a universe can lead to the birth of something much bigger. Just like a black hole, this cosmic collapse might be the beginning of something new on the other side. Some researchers imagine this happening in a higher dimensional space. We're used to thinking in 3 dimensions: up, down, left, right, forward, back, plus time. But some theories of physics suggest there could be more dimensions, ones we don't experience directly. In a space with more dimensions, it's possible that our entire universe could collapse into something that looks like a black hole, not inside our own space, but inside this larger one. From that outside perspective, our universe would look like a massive object shrinking and collapsing. But from the inside, from our point of view, the result might be the start of a new expanding spacetime, like another Big Bang. This kind of idea shows up in a few different theories. One is the cosmological natural selection. Every time a black hole forms, it could create a baby universe on the other side of its event horizon. That universe might have slightly different laws of physics than ours. Maybe a different mass for particles, a different strength of gravity, or a different mix of forces. If that's true, then universes might behave like living systems. The ones that are good at making black holes would create more offspring. Universes that aren't good at making black holes would create fewer, and eventually disappear. Over time, this would lead to a kind of cosmic evolution. Universes like ours, with just the right ingredients to form stars and black holes, would become more common through this strange form of natural selection. Another version of the idea comes from loop quantum cosmology, where the end of one universe naturally leads to the beginning of another. Some models go even further. They suggest that each black hole formed in our universe could lead to a new, separate universe. A universe branching off from ours, disconnected in space and time. From inside, it would look like a fresh beginning. But from a larger view, it would be just one leaf on a growing tree of universes. In this model, reality is a multiverse, a vast collection of universes, each born from the death of another. But where is all this happening? If a collapsing universe becomes a black hole in a higher dimensional space, what is that space? What does it mean for one universe to exist inside another? We don't have good answers yet. These ideas push the limits of our understanding. They ask us to think beyond what we can observe, and beyond what our current math can fully describe. If black holes give birth to new ones, and those universes have stars that form black holes of their own, then the process could go on forever. Each universe creates more black holes, and each black hole becomes a new universe. It's a cosmic chain reaction, not just stars and galaxies forming and dying, but entire universes giving rise to others. Over time, a whole ecosystem of universes could grow, each connected in ways we can't yet measure or see. Some physicists call this the fecund universe idea, a universe that is fertile, always giving birth to others. In that view, our universe is just one of many, part of a larger pattern that stretches beyond our horizon and our timeline. These other universes might be forever beyond our reach. But if they exist, then we are part of something far greater than we ever imagined. If universes evolve by creating more black holes, then maybe that's why the laws of physics seem so finely tuned. The strength of gravity, the masses of particles, the forces between them, all of these could be shaped by the need to form stars and black holes. In other words, our universe might not be lucky. It might be the product of a long cosmic history. How could we know we're inside a black hole? If we are living inside a black hole, the most obvious question becomes, how would we ever know? From where we stand, the universe feels huge, open, and full of galaxies drifting apart. We see the cosmic microwave background stretched across space, and we measure light coming from billions of light years away. But none of that tells us what's beyond the visible universe. It also doesn't tell us what space-time really is at the largest scale. So if the entire universe is just the inside of a black hole, what clues would be left behind for us to notice? The first thing to understand is that we wouldn't see the edges. If we are inside a black hole, the event horizon would be beyond anything we could ever detect from inside. The space itself would curve in such a way that light, and everything else, bends inward forever. From our perspective, the universe would seem endless, even though it's actually bounded. This might already match how our universe behaves. We don't see an edge. Instead, we see galaxies fading into the distance, redshifting more and more until they become invisible. Could that effect, the cosmic redshift, be a sign of deep curvature caused by a surrounding black hole? Some researchers think so. They've pointed out that the mathematical equations that describe the expansion of space in our universe look surprisingly similar to the equations that describe the space inside a rotating black hole. In both cases, space doesn't just sit still, and time doesn't pass at the same rate everywhere. That similarity might not be a coincidence. It could be a clue that our entire cosmos is shaped by the conditions set at the birth of a black hole. Another clue might come from the large-scale shape of the universe. If we could measure the full geometry of space, not just locally but across the entire cosmos, we might discover something unexpected. For example, if the universe is closed, meaning it curves back on itself like the surface of a sphere, that could suggest it's a finite region wrapped up in higher dimensional space. A black hole interior could match that shape. It would be a bounded volume with its own internal geometry, disconnected from the space outside. There are also questions about entropy and information. Inside a black hole, the amount of information it can store is proportional not to its volume, but to the area of its event horizon. Some have wondered if our universe might also be holographic. If this turns out to be true, it would be a massive clue that we are living in a space shaped by black hole physics. Other potential clues could come from cosmic background radiation. The early light from the universe, left over from the Big Bang, is one of the oldest things we can observe. It's been stretched over billions of years into microwave wavelengths, forming the CMB. But small patterns and irregularities in that light could tell us something deeper. If our universe was formed from matter collapsing into a black hole, the turbulence, rotation, and energy involved might leave imprints in that early radiation. Small asymmetries or unexpected alignments could be signals from that earlier phase. There's also the idea of black hole spin. Most black holes spin because the stars that formed them were already rotating. If a spinning black hole forms a new universe, that spin might influence the direction of expansion or the motion of galaxies. So if we detect a large-scale rotation in the structure of the universe, even just a small one, it might be a sign that our cosmic home began with angular momentum inherited from a parent black hole. Another way to think about it is to ask, what if we find something missing? The universe we observe follows rules, but it's also full of puzzles. Dark energy is one of the biggest. It seems to push the universe apart, faster and faster, but we don't know what it is. If our universe is the interior of a black hole, maybe dark energy is not a substance but a property of that curved space. In this view, the accelerated expansion is just what space does when it's trapped in a deep gravitational well. Instead of needing a mysterious force, we might just be seeing the effects of being inside a different kind of structure. If we find evidence that space and time are not continuous, but made of tiny bits, a kind of pixelated universe, that might fit with the idea that the universe has an information budget. And black holes, by their nature, put a strict limit on how much information can fit into any region of space. If the rules of quantum gravity eventually confirm this limit on all of space, It could support the idea that we're inside a larger system with boundaries, like a black hole. Even certain high-energy cosmic rays might carry hints. If we ever detect particles with energy above a certain cutoff, or if we fail to detect them when theory says we should, it could point toward extra dimensions or boundary conditions that we haven't considered. Some of these effects might only make sense if our entire visible universe is curled up inside a higher dimensional object, like a black hole. There's no simple experiment to prove it. We can't send a probe to the edge of the universe and try to escape. We can't step outside and look back. But we can look for patterns, places where our universe doesn't quite behave the way a free, unbounded space should. If those patterns match the predictions of black hole interiors, it would change everything about how we understand reality. The firewall hypothesis. Do black holes burn you alive at the horizon? In recent years, physicists have tried to understand the fine details of black hole evaporation using tools from quantum computing and entanglement. One key concept is something called the Page curve, named after physicist Don Page. It's a graph that shows how much information is hidden in a black hole over time. At first, the black hole looks like it's erasing everything, but then, after a certain point, the radiation starts to carry more and more information. By the time the black hole finishes evaporating, the information is back. It's not gone, just delayed. This suggests that black holes might act like very complex quantum computers. They scramble information in extremely complicated ways, but they don't destroy it. Figuring out how they do this is still an open question, but researchers have made progress by using toy models, simplified versions of black holes that can be studied with math. Some of these models reproduce the Page curve. Others show that information can leak out slowly through patterns of entanglement between the black hole and the radiation. Not everyone agrees, though, with some physicists arguing that there must be a sharp change at the edge of the black hole, a firewall of energy that burns up any information trying to pass through. This idea solves the information paradox by saying that the black hole doesn't have an interior in the way we thought. The smooth crossing through the event horizon of a black hole is part of what's called the equivalence principle, a foundation of general relativity. It says that in freefall, you wouldn't feel gravity. You could drift past the event horizon of a huge black hole without pain or drama. Eventually, you'd reach the center, where space itself ends, the singularity, and that's where the real trouble would begin. But the journey there would feel calm. Instead of a smooth and quiet horizon, the firewall idea says the edge of a black hole might be an invisible wall of blazing hot energy. If this idea is correct, then crossing the event horizon wouldn't be peaceful. It would be instant death. The moment you touch the horizon, you'd be incinerated by pure energy at the boundary itself. According to quantum theory, you can't have the same piece of information entangled in two different places at the same time. This is sometimes called the monogamy of entanglement. If the outgoing Hawking radiation is entangled with earlier radiation, which is needed to preserve information, then it can't also be entangled with the stuff still inside the black hole. That breaks one of the most basic ideas of how black holes were supposed to work. So physicists were left with a painful choice. If they wanted to keep the rules of quantum mechanics, if they wanted information to survive, then they might have to give up something else. And that something was the smooth horizon. That's where the firewall idea was born. In 2012, a team of physicists, Ahmed Almheri, Donald Marolf, Joseph Polchinski, and James Sully, proposed that to resolve the conflict, the event horizon might be transformed into a wall of high-energy particles. They weren't saying this would be visible from the outside, but for anyone falling in, it would mean instant destruction. Their paper sparked huge debate. Why? Because if the firewall exists, then the equivalence principle breaks down. Space-time wouldn't be smooth. The gentle ride across the horizon would be replaced by a sudden and violent shock. General relativity would no longer be safe in that region, and the idea that gravity is just curved space-time would be shattered. That's a heavy price to pay, even for saving information. It suggests that gravity, as we know it, stops working at the very edge of a black hole. And if that's true, then our whole understanding of what black holes are might need to be rebuilt. But not everyone accepts the firewall idea. Some physicists think it's too extreme. They argue that we might be missing a piece of the puzzle, something that would let quantum mechanics and general relativity work together without needing a firewall. One suggestion is that the laws of quantum physics might be even more flexible. Maybe information can escape black holes in other ways. Or maybe our ideas about entanglement need to be updated when gravity gets involved. There's also a possibility that the structure of space-time itself is not fundamental, that it emerges from something deeper, like patterns of quantum entanglement. In that case, the whole argument that leads to firewalls might be based on a wrong assumption. Perhaps black holes and their interiors are secretly connected to their Hawking radiation through hidden bridges in space-time. This concept has been called ER equals sign EPR, after Einstein-Rosen, the ER, and quantum entanglement, the EPR, for Einstein-Podolsky-Rosen. In this view, entangled particles are connected by microscopic wormholes. If true, then maybe the interior of the black hole is still connected to the outside world. If wormhole connections can carry information out, then maybe we don't need firewalls. Maybe the black hole can stay smooth and information can still escape, not through a wall of fire, but through the hidden links of spacetime itself. If firewalls are real, then the most basic assumptions about space and time break down at the edge of black holes. If they're not real, then we still have a paradox to solve. This is why black holes push physics to its edge. They're testing grounds for our most important ideas. Whether the event horizon is smooth or burning will tell us something deep about how the universe works. Right now, we're still looking for the answer. Can we decode the inside by watching the outside? Hawking radiation is made up of particles that are created just outside the event horizon. These particles form because of quantum uncertainty, the idea that empty space is never truly empty. For a brief moment, a particle and its partner can pop into existence. Usually in the vacuum of space, they annihilate and vanish instantly. But near a black hole, one can fall in while the other escapes. That escaping particle becomes real, and the black hole loses a tiny bit of mass to let it go. This is how black holes slowly shrink. It's an extremely slow process. For something like a black hole the size of a star, it would take longer than the age of the universe to fully evaporate. At first, Hawking thought the radiation carried no information. It was random, like heat coming from a stove. But if that's true, then the information about whatever fell into the black hole would be lost forever. To fix this, some physicists started to suggest that Hawking radiation isn't random after all, that maybe it carries hidden information that we haven't figured out how to detect yet. Reading that message is incredibly hard. The radiation is weak, and the black hole itself is changing as it radiates. The shape of its event horizon wobbles and shifts. Its surface vibrates. And that brings us to a second potential clue. Not just the light coming off a black hole, but the sound it might make. Of course, we can't hear black holes in the usual sense. They don't make sound in air, but they do ring in space-time itself. When two black holes merge, they send out ripples in space, gravitational waves. These waves carry a signature of the black hole's size, spin, and shape. And after the merger, the final black hole settles into a new form, ringing like a struck bell. These vibrations are called quasi-normal modes, patterns that fade over time but carry deep information about the black hole that created them. Scientists have already detected these waves using observatories like LIGO and Virgo. From just a few seconds of vibration, they've been able to measure the mass and spin of distant black holes with surprising precision. Some physicists believe that in the future, we could detect even more delicate patterns in these vibrations, maybe even ones that hint at the structure of space inside the event horizon. This approach, watching how black holes shake and shine, might be the only way we'll ever see inside. If the outside wobbles in just the right way, or gives off light in a certain pattern, it might reveal the secrets hidden inside. But if no signal can escape the inside of a black hole, how can the outside show us anything about it? One answer is that black holes don't have to send signals from the inside. Instead, the outside might be shaped by the inside from the start. The idea here is that information is somehow smeared across the surface of the black hole. Everything that falls in might leave a kind of imprint on the event horizon itself, changing how it behaves, how it radiates, how it vibrates. If we can decode that data, we could learn what's happening inside without ever going in. This principle came from string theory and was strongly influenced by studies of black holes. When physicists tried to count how many possible states a black hole could have, how many ways it could contain matter and energy, they found that the total didn't scale with volume, instead scaling with surface area. That would mean Hawking radiation, gravitational waves, and even the way black holes pull on nearby stars could all be affected by this hidden information. The outside behavior of the black hole would reflect the story of what fell in, not perfectly, but in a way that might someday be decoded. There's also work being done on black hole hair. For a long time, physicists believed black holes had no hair, meaning they could be described by just a few numbers: mass, spin, and charge. But recent ideas suggest that might be too simple. Maybe black holes do have more detailed features, subtle differences that reflect the unique things they've swallowed over time. If that's true, then the outside world holds a richer record of the past than we ever thought. If we can figure out how to read the signals from black holes, if we can learn to treat them not as cosmic erasers, but as cosmic mirrors, then we might finally understand what happens to information in our universe. And that information might just explain everything else, too. How far could gravitational waves let us peer inside? The discovery of gravitational waves in 2015 was one of the biggest breakthroughs in modern science. Until then, everything we knew about space came from light, visible light, radio waves, X-rays. But black holes don't give off light. They're invisible. That's what makes gravitational waves so special. They don't bounce off walls or get absorbed by dust. They pass through everything, untouched. That makes them a new kind of tool, one that might let us probe the deepest, darkest parts of reality. Every black hole merger sends out a burst of gravitational waves. At first, there's the in-spiral, the long, slow dance as the black holes spiral toward each other. Then comes the merger, the violent crash when they slam together. But the most mysterious part comes after that, during what's known as the ring down. This ring down phase is when the new, larger black hole settles into shape. It's like a bell that's just been struck. It sends out a clear tone, and hidden in that tone might be the keys to the puzzle we've been chasing for decades. The sound of the ring down, in gravitational wave terms, is made up of quasi-normal modes. These natural frequencies tell us something about the black hole's mass, spin, and size. But some wonder if those frequencies also depend on what's inside the black hole, or at least how the interior behaves during the merger. If all black holes were exactly the same on the inside, just empty pits ending in singularities, then we'd expect their ringdowns to all look the same too, as long as mass and spin were the same. But if there's more going on inside, if black holes have different internal structures, or even store information in unusual ways, then the gravitational waves might carry traces of those differences. That would mean there is a fingerprint, a signature. And if we learn how to read that signature with enough precision, we might start to tell different types of black holes apart, not just by size or speed, but by what lies beneath the surface. So far, our gravitational wave detectors have picked up dozens of mergers. They've confirmed that black holes exist and behave mostly as Einstein predicted. But we're still just scratching the surface. The signals we've detected are short and often noisy. The ring-down phase lasts only a fraction of a second, and the waves are incredibly subtle by the time they reach us, having traveled across millions or even billions of light years. But technology is getting better. Future observatories like the Einstein Telescope in Europe or the space-based LISA mission planned by the European Space Agency could dramatically improve our sensitivity. LISA, in particular, will orbit the Sun and listen for lower frequency waves, the kind created by supermassive black holes at the centers of galaxies. These signals are much slower and longer lasting. That gives scientists more time to study the ringdown in detail. Maybe quantum effects show up in the way black holes vibrate. Maybe different theories of gravity predict slightly different tones. If so, gravitational waves could help us test those theories, not in a lab, but using the universe itself as an experiment. One wild idea is that if black holes don't have true event horizons, if, for instance, there's something else just outside them, like a fuzzball or some kind of exotic matter, then the ringdown waves would echo. Instead of dying out smoothly, the signal would bounce and return like a faint aftershock. These echoes would be very weak and hard to detect, but they might carry clues about the stuff just outside, or even inside, the black hole. Several teams have looked for these echoes in the data. So far, the results are mixed. No clear evidence, but also no clear refutation. If echoes are real, they could be one of the biggest signs that black holes are not as simple as we once thought. But proving they exist will require much more precise measurements and many more observations. The black hole's gravitational pull affects things outside it, even though the mass is inside. That means the black hole's structure, including its changing shape during a merger, can ripple outward. Those ripples, gravitational waves, don't carry particles or energy from the inside directly, but they reflect how the whole system moves and shifts, and that includes what's going on near the horizon, maybe even just beneath it. It's like watching the surface of a drum. You can't see what's inside the drum, but the way the surface shakes tells you a lot. How tight the skin is, how deep the drum is, even what might be bouncing around inside. In the same way, by studying black hole vibrations, we might begin to infer things about their interiors, not directly, but through their influence on the outside. Gravitational waves from a merger don't arrive all at once. They come in a sequence, with some parts traveling faster than others, depending on how the space around the black hole is warped. That timing contains information. Tiny delays and changes in the wave patterns might help us map the black hole's properties with incredible detail. It's still early days. Right now, we can tell if a black hole merger happened, and we can measure some basic features of the result. But in the future, with more data and better models, we may be able to go much further. We might start to build a catalogue of black hole voices, each one singing its unique ringdown tune. And just like voices can hint at emotion, health, or history, these tones might someday hint at the internal story of each black hole. The promise is enormous, the chance to turn black holes from silent enigmas into storytellers. And the universe has many stories left to tell. Are black holes actually wormholes in disguise? If the right conditions exist, it's possible, at least on paper, to fold space-time in such a way that two separate regions become directly connected. Picture space like a sheet of paper. If you draw two dots far apart and then fold the paper so those dots touch, a hole punched through would take you instantly from one dot to the other. That's what a wormhole does. It shortens the distance by bending reality itself. The problem is, wormholes aren't supposed to be stable. In the early versions of the equations, they collapse before anything can pass through. The walls fall in, the tunnel pinches shut. But later, theorists discovered that if you could somehow hold the tunnel open with a kind of negative energy, something that pushes outward instead of pulling inward, the wormhole could stay open long enough to be used. Some versions of these wormholes look very similar, from the outside, to black holes. They have an entrance. They bend light around them. They have what appears to be an event horizon. But if you fell into one, instead of being crushed by gravity at the center, you might pass through to somewhere else entirely. From a distance, it would be hard to tell the difference. A wormhole entrance could look exactly like a black hole. Same mass, same gravitational pull, same shadows when viewed against glowing gas. The only difference might be in how it behaves over time, how it moves, how it interacts with things nearby, and maybe even how it vibrates. a wormhole might cause small signals to bounce back and forth across the tunnel before fading away, creating repeated ringing patterns that a regular black hole wouldn't produce. If something approaches a black hole, we expect it to disappear beyond the event horizon. But if it falls into a wormhole, there could be odd signs, like delayed radiation, flickering jets of matter, or even gravitational tugs from the other side of the tunnel. These effects would be incredibly hard to detect, but they might leave a faint fingerprint in the data. There are also theories that explore the possibility of traversable wormholes, which are wormholes stable enough to travel through safely. Some of these ideas suggest that exotic particles, or certain effects from quantum physics, could hold the tunnel open. One theory even suggests that entangled particles, the strange twins of the quantum world, could be connected by tiny wormholes. The modern interpretation of ER equals sign EPR is that maybe the two concepts are connected, that a wormhole is just the geometric version of entanglement. In other words, every pair of entangled particles might be linked by a tiny wormhole, and the bigger wormholes we imagine might be made up of vast networks of these microscopic connections. If wormholes connect different universes, not just different parts of our own, then a black hole in our universe could be linked to a region in a parallel reality. When something falls into that black hole, it doesn't get crushed. It exits into an entirely different cosmos, with different laws, particles, or even dimensions. These inter-universe wormholes could be like cosmic transport hubs, moving matter and energy between worlds that will never otherwise interact. Could we ever travel through one? That's hard to say. Even if these wormholes exist, they might be incredibly small, smaller than an atom. Others might be enormous, but unstable. Getting through without being ripped apart by gravity, radiation, or tidal forces would be a challenge beyond anything we've ever tried. Still, if even one natural wormhole exists and could be kept open long enough, it might become the most important discovery in the history of science, the first true portal. But how could we prove that any black hole is a wormhole in disguise? The best telescopes in the world can't see inside the event horizon. Even the famous image of the black hole in M87, taken by the Event Horizon Telescope, only shows the silhouette. We don't see the structure beneath, so scientists have turned to more indirect methods. They're trying to build models, simulations, to compare how wormholes and black holes would behave under certain conditions. The idea is to look for subtle mismatches, a flicker of radiation that shouldn't be there, a gravitational echo that rings twice instead of once. The darkest objects in the universe, long thought to be symbols of destruction, might turn out to be pathways. The ultimate blind spots could hide doors we never knew existed. And if we ever find a way to unlock one, to step through, or even just send a signal across, we might finally discover what lies beyond the edge of our known world. Falling into a black hole, could you survive the trip? Falling into a black hole sounds like a one-way ticket to destruction, and in most cases it would be. A small black hole with only a few times the mass of our Sun would tear you apart long before you ever reached the event horizon. The tidal forces would spaghettify you quickly and violently. But what if the black hole is much, much bigger? A supermassive black hole has a very different gravitational profile. The tidal forces near the event horizon of such a giant are much weaker because the curvature of space-time changes more gently. The gravitational gradient across your body isn't so extreme. In theory, you could fall past the event horizon of a supermassive black hole without noticing anything unusual. There would be no obvious moment when everything changes. Of course, that silence would be part of the problem. No signal, no light, no information can escape from inside the event horizon. You wouldn't be able to tell anyone what you're experiencing. You could send a radio message just before you crossed over, but nothing beyond that moment would ever reach the outside world. But what would it actually feel like? Assuming you're falling toward a supermassive black hole, and you start from a safe distance, you'd accelerate slowly, pulled more and more by gravity. The stars behind you might start to stretch or distort due to gravitational lensing. The black hole itself wouldn't look like a hole. It would look like a dark circle, maybe glowing around the edges from the disk of hot gas swirling nearby. As you got closer, light from behind the black hole would bend around it. You'd see warped images of the universe. The sky would begin to twist. Time would seem to slow down for everything around you. But for you, it would move normally. Crossing the event horizon would just be a point in space where the escape velocity becomes faster than the speed of light. If you looked back, the outside universe would look more and more compressed. Light from distant stars would shift into deeper and deeper red. Eventually, the outside might fade entirely, until all you could see was blackness behind and even deeper blackness ahead. Inside the event horizon, your fate depends on the nature of the singularity. In traditional models, once you cross the horizon, your path always leads inward. No matter how much you struggle, everything is pulled toward the center. But some theories suggest that the singularity might not be a true point. Quantum effects might somehow smear out the singularity, or create a kind of core that doesn't destroy everything instantly. If that's the case, then the trip inside a black hole could be longer and more complex. You might not just be crushed the moment you cross the horizon. You might drift, fall, pass through strange curved regions of space-time, and only much later face the end, or a new beginning. Some physicists have played with the idea that black holes might act like time machines of a sort. Because of how time slows near the event horizon, someone falling into a black hole could, in theory, witness the future of the universe unfolding at high speed. Galaxies might drift apart, stars might burn out, civilizations might rise and fall in what, to the falling observer, would feel like just minutes. So while falling into a black hole is often described as a quick and violent death, the truth is more complex. In a massive black hole, you might have minutes, hours, or even longer before you reach the central region where things become deadly. Those final moments could be quiet, surreal, even beautiful, a kind of eerie calm as the laws of physics begin to blur. Could negative energy be the key to entering a black hole safely? In quantum physics, especially in the field of quantum field theory, the idea of negative energy has shown up more than once. It doesn't behave like normal energy, which always adds something to a system. Instead, negative energy can subtract. Normally, gravity from a black hole grows stronger, warping space and time so that every path leads toward the center. But what if you had a way to push back against that warping? What if, instead of being pulled inward and stretched apart, you could somehow level out the force of gravity? This is where negative energy comes into the picture. In theory, if you surrounded yourself with a field of negative energy, it might act like a kind of bubble or cushion. As the gravitational pull tried to increase, the negative energy could reduce the net effect. Instead of being stretched or crushed, you might feel neutral, floating even, as if gravity were cancelled out or reversed around you. Some scientists describe this in terms of exotic matter, which isn't made of atoms like we're used to, but instead follows strange rules that allow for negative pressure or energy density. The Casimir effect is often brought up when discussing negative energy in real physics. In this effect, two very thin metal plates are placed extremely close together in a vacuum, a space with no matter. Because of quantum fluctuations, the empty space between the plates actually ends up with less energy than the space outside. That difference acts like a small amount of negative energy. It's a tiny effect and only measurable with sensitive instruments. But it shows that the vacuum of space can, under the right conditions, behave in ways that bend our expectations. So if negative energy is real, could we use it to explore a black hole? Right now, we have no way to produce large amounts of negative energy or shape it into something usable. The Casimir effect happens on incredibly small scales. To protect a spaceship, a person, or even a computer probe, you'd need a much larger field. You'd also need to stabilize it. Negative energy tends to be unpredictable. It doesn't sit still. It shifts and flickers like a candle flame in the wind. Harnessing it would require a technology far beyond what we have today. Some theories have tried to get around this by imagining clever workarounds. One idea is to use negative energy not as a shield, but as a tool to change the structure of space itself. This ties into concepts like wormholes and warp drives, ideas that would let you manipulate space-time so that dangerous areas like black holes become less dangerous. You wouldn't resist gravity directly. Instead, you'd shape the path ahead of you so it no longer leads to a deadly end. According to general relativity, creating a stable wormhole or warp bubble would require large amounts of negative energy, more than we know how to generate. And some researchers argue that even if you could collect enough of it, quantum effects would cause the structure to collapse quickly. In other words, nature might not allow it to last. Still, others believe that negative energy might exist in more places than we think. Some parts of the universe, like regions near black holes or in high-energy particle interactions, might naturally create short-lived pockets of negative energy. If that's true, then it's possible, just barely, that black holes already contain areas where negative energy plays a role. Maybe it helps shape the way the event horizon behaves. Maybe it influences Hawking radiation. Or maybe it just shows up and vanishes too quickly to notice. Let's imagine a more advanced civilization, 1,000s or even millions of years ahead of us. Suppose they've learned how to trap and control negative energy. They could, in theory, use it to create protective fields that cancel out the harmful tidal forces near a black hole. Their explorers might dive into the event horizon the way we dive into the ocean. Instead of being torn apart, they might coast gently into the unknown. Inside the black hole, negative energy might play another role. If space-time is warped into extreme shapes, a controlled field of negative energy could help steer through it. Like a rudder on a ship or a fin on a rocket, it could allow for adjustments, small changes in course. Instead of falling uncontrollably toward the singularity, maybe it would be possible to aim for a specific region, a stable core, a wormhole throat, or an alternate exit. Instead of being trapped, you'd pass through into another universe or another point in space. No one has built a negative energy generator. No one has tested a shield made of exotic matter. We don't even know if such technology is physically possible. The laws of the universe might forbid it. But asking these questions pushes us toward deeper understanding. They force us to test the edges of physics, to look for hidden truths buried in the math. Negative energy is one of those edges. It hints at hidden mechanisms in the vacuum, in the structure of space-time, and even in the way gravity might be linked to quantum fields. If we could master it, we might learn how to navigate not just black holes, but the deeper geometry of the universe. What string theory says about black hole interiors? String theory suggests that the smallest building blocks of the universe are tiny strings. These strings are incredibly small, much smaller than atoms or even the particles inside atoms. And they don't sit still, they vibrate, like the strings on a musical instrument. The way they vibrate determines what kind of particle they become. A photon, an electron, a quark. So instead of a particle being a dot, it's more like a loop or a strand. This small change in perspective could make a big difference near a black hole. If particles are really strings, then maybe they can't be crushed into a point. Maybe the idea of a singularity doesn't happen in the same way. Instead, the strings stretch, smear, and tangle, creating a kind of fuzzball or cloud. Some versions of string theory even call it the fuzzball model of black holes. In this model, the inside of a black hole is a mess of tangled strings. The event horizon might still exist, but there's no singularity waiting inside. Instead, the entire interior is made of vibrating strings packed together in extreme ways. It's still dangerous. The gravity is still intense. But the behavior of space, matter, and time might follow a different set of rules. Some strings might loop through extra dimensions, ones we don't see in daily life. These extra dimensions could fold, twist, or hide inside the fabric of space. They might even wrap up into tiny shapes called Calabi-Yau spaces. If those dimensions are real, then the inside of a black hole could be a kind of multidimensional network. This network would be made of the strings themselves. In string theory, strings can split and rejoin. They can carry energy, momentum, even charge. And in some cases, they can become higher dimensional objects called branes. A brane is like a stretched out version of a string. Not a one-dimensional line, but a two- or three-dimensional surface. Some theories even suggest our entire universe could be a brane floating in a higher dimensional space. So what happens when these strings and branes fall into a black hole? That's a question researchers have been trying to answer for years. One idea is that strings don't disappear when they cross the horizon. They might leave behind a trace on the surface. In string theory, the holographic principle gets a lot of attention. It shows up in the ADES-CFT correspondence. One side of the map is a space with strings, black holes, and curved geometry. The other side is a world with quantum fields, like the ones used to describe particles in a lab. Some physicists suggest that space itself, the thing we move through and live inside, is made from the links between strings. If this is true, then the inside of a black hole isn't just a location. It's a structure built from the way strings are woven together. Gravity, time, and motion are just side effects of how those strings interact. This could mean that the singularity is an illusion. We see it in general relativity because that theory looks at the universe as smooth and continuous. But when you zoom in far enough, smaller than atoms, smaller than protons, things aren't smooth anymore. They're made of strings, vibrating and stretching in higher dimensions. The singularity is just a misunderstanding. What really exists is a web of strings too dense for us to currently explore. Another interesting result from string theory is the idea that black holes might not be entirely black. If strings replace points, then maybe some of their energy can leak out, even from inside the horizon. This might be a new way to understand Hawking radiation. Instead of particles tunneling out of empty space, maybe the strings themselves wiggle in ways that allow a slow trickle of energy to escape. String theory itself hasn't been proven in the lab. Its equations are beautiful and far-reaching, but hard to connect directly to experiment. Still, it offers a powerful way to think differently about the universe and about black holes. If strings are real, and if space is made from their vibrations, then black holes might just be knots in the cosmic fabric, dense, complex, and full of hidden structure. The mystery shifts from a crushing singularity to a tangled song of strings humming in extra dimensions just beyond our view. Loop quantum gravity and the bounce hypothesis. There's another theory that challenges the traditional idea of a black hole, and it comes from a different direction than string theory. In loop quantum gravity, when gravity gets too strong, instead of tearing space apart or crushing it into a point, the loops begin to fight back. This force, which doesn't exist in standard physics, is caused by the structure of space. It acts like a spring, pushing against further collapse. When the inward pull of gravity and the outward push of the loop structure balance out, the collapse stops. And then, just as a compressed spring bounces back, the universe inside the black hole starts expanding. This process doesn't require exotic matter or new particles. It comes from rewriting gravity in a way that includes quantum behavior. General relativity doesn't include quantum effects. Loop quantum gravity tries to fix that by describing gravity itself as a quantum system. This is different from the fuzzball idea in string theory. In the fuzzball model, black holes don't have an interior at all. The entire mass of the black hole is stored in the outer region, tangled in strings. There's no space inside, and nothing gets through. In loop quantum gravity, on the other hand, there is an interior. Space still exists inside the black hole, and it changes as matter falls inward. The center becomes a place of extreme density, but not a point. It's a compressed core made of loops, and from that core something new can emerge. Another big difference is how the two theories handle time. In fuzzballs, time stops at the edge. You never get to see what happens next because there is no next. But in the bounce idea, time continues. The future of the collapsing matter isn't a frozen singularity, but a rebirth. This could solve the information paradox in a very different way. In the fuzzball picture, information is stored in the string structure and slowly leaks out as radiation. But in the bounce view, the information might go somewhere else entirely. It could pass through the bounce and become part of the new universe. That means information isn't lost. It's just no longer accessible to us. It's hidden behind a kind of cosmic curtain. If we were born from the bounce of a black hole in another universe, there might be tiny imprints in the cosmic background. These imprints could look like circles or patterns in the radiation that surrounds us. The bounce idea also suggests that black holes don't last forever. As they reach the quantum gravity stage, they could transform rather than evaporate. From the outside, this might look like a sudden disappearance. The black hole blinks out, leaving behind a strange burst of energy. That burst might be the last connection between the two universes, or it might be the moment when one universe gives birth to another. Some versions of this theory also hint that the inside of a black hole might not be totally disconnected from our world. There could be weak links, mathematical connections, between the new universe and ours, allowing subtle forms of communication or influence. These are ideas on the edge of speculation, but they push physicists to look deeper into the structure of space-time. Time inside a black hole. Does the future already exist? We already know that black holes stretch time, but what exactly happens to time as you approach the singularity? No one knows for sure. Some theories suggest that from the viewpoint of an object falling in, the entire future of the universe outside the black hole might play out in a flash. Because time runs differently inside the horizon, someone falling in might see the universe grow old in what feels like a blink. They might see galaxies evolve, stars explode, and even the end of time itself, all while falling toward the center. Others go further. They propose that inside the black hole, the future is not just something you're headed toward, it's already there. That's because, in general relativity, the universe doesn't evolve frame by frame like a movie. Instead, space and time together form a kind of four-dimensional structure, a block universe. In this view, past, present, and future all exist together, like pages in a book. You don't see all the pages at once, but they're all there. You move through them one at a time. Inside a black hole, this block universe idea might become more than a theory. The intense gravity and warped geometry could force time to flow in only one direction, toward a point that already exists in the future. In other words, the end of your journey inside a black hole might be fixed from the moment you cross the horizon. Your future is already written, and you're just playing it out. Is free will still possible in such a place? If time is just another direction in space, and you're sliding down it with no ability to stop or turn back, are you really making choices? Or are you just following a script laid out by the geometry of the universe? Some physicists argue that this deterministic view isn't limited to black holes, that it might apply to all of space-time. But black holes make the issue more obvious. Once you're inside, the flow of time feels like a physical force. It drags you along, whether you like it or not, and it takes you to a destination that seems to exist before you even get there. There are ideas from quantum mechanics that challenge this picture. In quantum theory, particles don't follow one fixed path. They explore all possible paths at once. The outcome isn't set until a measurement is made. Some physicists hope that a full theory of quantum gravity will soften the idea of a fixed future inside black holes. Maybe the singularity isn't really the end. Maybe quantum effects let you skip over it or avoid it somehow. But until that theory is fully developed, we're left with a haunting image. The idea that the singularity at the center of a black hole is not just a destination, but your final moment, waiting for you like a silent marker on the road of space-time. It knows you're coming. If black holes are connected to white holes, as some theories suggest, then time inside a black hole might flip. The flow might reverse. What seems like an ending from our point of view might be the start of something new from another. In that case, the singularity becomes a tunnel where time begins again, just in a different direction. In that version, The future is part of a larger loop, a cycle of collapse and expansion, compression and release. Black holes, white holes, even entire universes might be connected through these strange tunnels in space and time. The future might not just lie ahead, it might be behind, above, or next to us. These ideas stretch the limits of what we can test, observe, or even imagine. But they're based on the best theories we have. And they show that inside black holes, time itself is pulled apart, twisted and remade into something unfamiliar. If we're inside a black hole, why can't we escape? If we're inside a black hole, why don't we notice? Why doesn't everything fall inward towards some center? Why doesn't the sky go black? Why don't we see the walls closing in? One possible answer is that we are so deep inside that we can't see the event horizon anymore. Think of it like living inside a massive balloon. The walls of the balloon are too far away for us to detect. All we can see is the space inside, which looks flat and ordinary to us. From our perspective, it stretches endlessly in all directions. But if we could step outside that balloon, if we somehow escaped the black hole, we might see that we were always inside a curved space, hidden by an invisible boundary. Here's another way to think about it. Inside a black hole, the geometry of space and time changes. Distances become distorted, directions warp, and most importantly, time itself becomes tied to movement through space. Once you're inside the horizon, everything you do moves you closer to that moment. That includes sitting still, walking, thinking, even doing nothing. Now stretch this concept to the scale of the universe. The Big Bang is often described as the beginning of time. But from a different point of view, it might also look like the singularity at the core of a black hole. In this case, the singularity isn't behind us. It's what we came from. We're not falling toward it. We've already emerged from it. If the Big Bang was a time-reversed version of a black hole, then our universe might be the expanding interior of a region that formed when something else collapsed. But why can't we escape from it, if we're inside? The answer might be that escape doesn't mean anything in this context. From inside the universe, there's nowhere else to go. The universe isn't expanding into something else. It's expanding within itself. Space is growing. Galaxies are moving apart. But the overall geometry might still be shaped by something like an event horizon. The horizon just isn't visible to us because it's not outside of us. It's all around us, beyond the edge of what we can observe. In this view, the concept of outside the universe might not exist at all. Just like nothing inside a black hole can send a signal to the outside, nothing inside our universe can reach beyond the cosmic horizon. Inside a black hole, space can still feel normal, just distorted in ways we don't notice locally. A person falling into a giant black hole might experience miles of open space and even a sense of weightlessness, even though their fate is sealed. The size of the black hole matters. A large one gives you more room, more time, and a smoother ride, even as you're falling toward the core. If the universe is the inside of a cosmic black hole, then it's the biggest one possible. The event horizon could be billions of light years away, or beyond even that. The curvature of space would be too slight for us to notice directly. The expansion of the universe would feel like ordinary physics, but from a different point of view, we'd still be deep inside something massive, curved, and inescapable. Some physicists have taken the math of black holes and applied it to the universe as a whole. And the results are strange, but possible. Under certain conditions, the interior of a black hole can look just like a universe, with galaxies, stars, time, light, and laws of nature, all playing out inside a region that, from the outside, looks like silence. That might explain why every direction in space looks the same, why there's no sign of what came before the Big Bang. If the Big Bang was the birth of a space-time bubble, then we're inside that bubble, and always have been. The event horizon is not something we can fly toward. It's part of the geometry that surrounds us. So when we ask why we can't escape, maybe the answer is that we're already beyond the point of return. Some physicists have suggested that space-time can pinch off. This means that if a universe expands quickly enough inside a black hole, it might eventually separate completely from the parent. The tunnel that connects it, the black hole's throat, could collapse or break. After that point, the two universes would no longer be connected, even in theory. They'd become two completely separate regions of existence, each with its own time and space. This concept has been explored in some versions of quantum gravity, and it also appears in discussions of baby universes, theoretical objects that bud off from our own space-time and float away. In these models, a baby universe forms as a small fluctuation, grows, and eventually disconnects. After that, it's on its own. But for this to happen, the expansion of the baby universe must be faster than the inward pull of gravity at the black hole's core. And not just slightly faster, dramatically faster. Inflation must not only begin, but last long enough to stretch space to vast sizes before any collapse can catch up. If inflation fails, the baby universe might collapse back inward, ending in a singularity, a dead end. But if inflation succeeds, the universe grows beyond control. In this light, maybe we're already free. If our universe began as the interior of a black hole, and if inflation stretched our space beyond the size of that black hole's horizon, then we've already outgrown our origin. We're no longer bound. We're expanding into our own future, into a cosmos that may never know where it began. Still, the mystery remains. Is this all happening again, right now, in black holes all across the sky? Are countless new universes being born, each with its own rules, its own stars, its own questions? And could some of them be asking the same thing we are now, wondering if they too were born from something else, and if they ever escaped? Are quantum tunneling effects hiding the real interior? In everyday life, if you throw a ball at a wall, it bounces back. But on a quantum scale, if you throw an electron at a wall, there's a tiny chance it will vanish from one side and reappear on the other, as if the wall wasn't there. It doesn't go over or around. It goes through without ever being inside the wall. Now, take that idea and apply it to black holes. What if the event horizon isn't as solid as we think? What if, on a quantum level, particles can tunnel across it, in both directions? If tunneling works near the event horizon, then the inside of a black hole might be much more active. Particles that should be trapped forever might find ways to escape, and particles outside, including virtual particles that constantly flicker in and out of existence, might tunnel inward. That would mean the inside of a black hole isn't sealed off. It's connected to the rest of the universe. Some physicists have suggested that black holes might have more than one interior. Not just a central core surrounded by empty space, but layers, like an onion. These layers might form from different quantum states, each with its own energy, density, and curvature. Think of it like overlapping realities, stacked inside each other. Most of them would be unreachable in a classical sense. But with quantum tunneling, particles, or even bits of information, might pass from one layer to another. This could mean the interior of a black hole isn't a single region at all. It could be a network of quantum zones shaped by tunneling effects. Some of these zones might be close to the surface. Others might be buried deep in the geometry of the black hole. Some might be stable. Others could change constantly. And we would never see them from the outside. To understand how this works, we have to step into the concept of potential barriers. In quantum mechanics, a barrier is not always a physical wall. It's any region where the energy changes in a way that should stop a particle. But because particles act like waves, they don't always stop. The wave can leak into the barrier. And if the barrier is thin or the energy is just right, the particle can reappear on the other side. Inside a black hole, the geometry of space and time creates many such potential barriers. The enormous gravity, the curved space, the changing time direction, all of it forms zones that should isolate regions from each other. But if tunneling can happen, then particles might drift through these regions, creating connections we can't see. One idea that comes out of this is the possibility of hidden interiors. These are parts of the black hole that can't be reached by ordinary falling. If you fell into a black hole in the usual way, you'd follow a path into the singularity. But quantum tunneling might allow for sideways paths, hidden routes through the quantum structure of the black hole. A particle might vanish from one region and reappear in another, skipping over the deadly core entirely. Maybe the singularity is just one endpoint. Other regions could exist nearby, but out of reach unless tunneling occurs. These regions might hold energy, information, or the seeds of new universes, but they would be invisible, hidden behind quantum barriers. Some researchers have even tried to describe these ideas using string theory and quantum gravity. This creates a foamy, jittery background, and in such a space, tunneling might be a natural part of how the geometry works. The black hole interior would then be more like a storm of overlapping spaces, each one built on quantum rules. If this is true, then the inside of a black hole is a place full of structure, layers, bubbles, fluctuations, and links to other parts of space-time. And tunneling could be the key to moving through it. If particles can tunnel inside a black hole, what happens to the information they carry? If tunneling lets particles move between quantum layers, then maybe that information is preserved, just in a place we can't see. It wouldn't escape the black hole completely, but it wouldn't be destroyed either. It would be hidden in the folds and ripples of the quantum interior. It's possible that the entire interior of a black hole is shaped by this kind of quantum process. That would make the idea of a smooth fall into a singularity too simple. Instead of a clean journey to a final point, it would be more like navigating a quantum maze, one where the rules are constantly shifting and where unexpected shortcuts open and close without warning. Some theories suggest that tunneling might not just be a feature of black holes. It could be how new universes form. When matter collapses into a black hole, it might reach a point where classical gravity breaks down. At that moment, quantum effects take over, and instead of forming a dead singularity, the black hole might tunnel into a new state, a new region of space-time that inflates into a baby universe. Quantum tunneling would be the bridge between these realities, the hidden passage that links what we see to what lies beneath. The observer effect taken to the extreme. In quantum mechanics, there's a strange rule that sounds more like philosophy than science. Observing something changes it. At the smallest scales of nature, just the act of measuring, or even being able to measure, can shift what happens. It's called the observer effect, and it sits right at the center of quantum theory. Particles like electrons and photons don't have fixed positions or speeds until they're measured. Until that point, they exist as clouds of possibilities, spread out in space, described by probabilities. But the moment a measurement happens, that cloud collapses. The particle is suddenly there, with specific properties. It's as if the universe is waiting for someone to look before deciding what's real. This idea has caused endless debates. Some physicists think it's just a quirk of how we describe things, not a sign that consciousness is involved. Others wonder if there's something deeper going on, a link between awareness and reality itself. But wherever you fall in the debate, one thing is clear. Quantum systems don't behave like solid clockwork machines. They're slippery, flexible, and unpredictable until someone or something observes them. Now imagine taking that principle and applying it to a black hole. Black holes are built on gravity, space, and time, the language of Einstein. But the quantum world is very different. It works with jumps, fuzziness, and uncertainty. Somewhere, deep inside the math, these two worlds must come together. What if observation itself plays a role in how black holes behave? Not just from the outside, but from the inside too. Picture this. A black hole without any observers is just a region of warped space-time. Everything inside it follows the laws of general relativity. It curves inward, light can't escape, and time runs toward a singular end. But what happens when you drop a conscious observer into it? From their perspective, they fall through the event horizon without feeling anything unusual. But their presence changes things, not physically, They don't push on the space-time fabric in any big way. But quantum mechanically, they bring something new, the capacity to observe. That might seem like a stretch. After all, how could just being aware change the structure of a black hole? But in quantum theory, it's not awareness in the human sense that matters. It's the possibility of interaction. The moment a system could, in theory, be measured, even if no one actually performs the measurement, the rules shift. The probabilities collapse into one path. The fuzziness turns into something definite. In a black hole, this might mean that certain quantum states inside don't settle until an observer is there. Until then, the interior could exist in a superposition, a kind of cloud of all possible configurations. The space inside might be flat, curved, spinning, or even branching. But once someone crosses the event horizon and starts to measure, all that possibility snaps into a single reality. This takes the observer effect to an extreme. Instead of affecting particles or atoms, it could affect space itself. The very shape of the black hole's interior might depend on how it's observed, or whether it's observed at all. There are even ideas in physics that lean in this direction. One of them is complementarity, where two different observers can have totally different views of what's happening, and both can be correct within their own frame of reference. If these realities both exist, then which one is real? The idea of complementarity suggests we might need to give up on having one fixed answer. Reality could be observer-dependent. Now imagine not just observers watching black holes from a distance, but observers actually inside them, moving, thinking, and making measurements. The structure of the black hole's interior might shift as they move, not like walls forming or tunnels appearing, but in terms of quantum geometry, space might rearrange itself slightly based on what's being measured. Time might stretch differently. Events that were blurred into uncertainty might snap into place. There are some interpretations of quantum mechanics that support this kind of thinking. The relational interpretation, for example, says that properties like position or energy don't exist on their own. They only exist in relation to something else, especially an observer. That could mean the space inside a black hole isn't absolute. It's defined by the relationships between whatever's inside and whoever's looking. This would make every black hole interior unique, not just because of how it formed, but because of who or what ends up inside it. Two black holes with identical mass, spin, and charge might still have different interiors, shaped by different observers falling in at different times. Each journey would form a kind of personal version of space-time created on the spot. Some theories go even further. They suggest that space-time itself isn't a fixed backdrop, but a result of quantum entanglement. If that's true, then observation doesn't just change the contents of space. It helps create space. And in a black hole, where extreme conditions strip everything down to its barest structure, this effect could be magnified. This would mean that the inside of a black hole isn't something waiting to be discovered. It's something that forms through the act of experiencing it. The moment an observer crosses the horizon, their presence reshapes what exists. And this could explain why we can't create a full map of a black hole's interior. It's because there is no single map. Each journey through a black hole is different, depending on the path taken, the interactions made, and the observations performed. The interior is not a fixed place. It's a living process, built through quantum relationships. Even time itself might be part of this process. From the outside, black holes seem frozen in time. But from the inside, time still flows, though maybe not in a straight line. Observation might guide the flow of time, steering it towards certain outcomes. The sequence of events could depend on what's being noticed and in what order. So is there such a thing as an unobserved reality inside a black hole? Does anything exist before it's measured? And if the observer effect really plays a role at this scale, could the universe itself, possibly inside a larger black hole, be shaped by observers within it? If so, the universe may not be a static machine. It could be a responsive, flexible system, one that changes based on how we interact with it. Black holes, rather than being distant, dead zones, could be places where this process is most obvious, places where reality emerges moment by moment. If our universe is inside a black hole, what's outside? The moment we imagine our universe as a kind of bubble, we start to wonder what surrounds that bubble. What kind of reality gave rise to our own? If our entire universe began as the collapse of some massive object in another universe, then that larger universe must have had its own stars, its own gravity, and its own physical laws. And somehow, one of those stars collapsed into a black hole so powerful that it created an entire universe on the other side. To an outside observer from the parent universe, the black hole just sits there, dark, dense, and quiet, except for maybe some Hawking radiation leaking out slowly over time. But on the inside, there would be an entire cosmos unfolding, galaxies forming, stars igniting, life evolving. Billions of years could pass in here, while from the outside, almost no time goes by. Time itself might flow differently between the two. This makes the parent universe feel even more mysterious. Is it older? Is it still active? Has it continued on without us, or did it end when our black hole was formed? If our universe is still expanding, that suggests the energy that triggered the expansion hasn't run out yet, but it doesn't tell us what happened on the other side of the event horizon. The parent universe might be completely different from ours, or it might be strangely familiar. One idea is that each child universe inherits certain properties from the parent. Maybe the mass, spin, or charge of the black hole in the parent universe affects the initial conditions in the child. For example, if the black hole was rotating, it might set the new universe spinning. If it had a certain amount of matter, that might decide how much energy is available in the new universe. This would make each universe a kind of fingerprint of the black hole it came from, shaped by what was swallowed, yet evolving independently after birth. But that also means the parent universe could have been very different. Maybe its physics allowed for different kinds of matter. Maybe stars were much larger, or black holes were easier to form. Or maybe it was governed by rules we wouldn't recognize. Our universe may feel normal to us, but from the outside, it might be seen as strange, rare, or even unstable. Is our universe unique? If the parent universe has many stars, and many of those stars have collapsed into black holes, then it might have given birth to many universes. Ours could be one of billions, each formed from a different black hole, each evolving separately. That parent universe might be a kind of cosmic nursery, constantly seeding new realities. Some thinkers imagine the parent universe as unimaginably vast, maybe much larger and older than ours, filled with strange structures and exotic forms of life. Others think it might no longer exist, having collapsed or faded long ago. In that case, our universe might be the only trace left, a kind of fossil of a larger cosmic event, now isolated and drifting through its own version of time. And if our universe contains black holes, which it does, then maybe we're a parent universe now too. This creates a kind of family tree of universes, with ancestors and descendants, each linked through black holes. The branching could be infinite, not in space, but in space-times, each one its own separate reality. If this is true, then the outside of our universe isn't just empty space or some other dimension. It's a whole other universe, with its own galaxies, its own black holes, and its own story. That universe might have an outside too, and so on, endlessly. But what about the largest possible outside? If our universe is inside a black hole, and that black hole is inside another universe, and so on, is there an ultimate reality beyond all of them? A final container? Or is it nesting all the way up, with no top, just as there may be no bottom? It's hard to know, because we only have access to our own bubble. Our instruments, our telescopes, and even the laws of physics we observe are shaped by this universe. We can't test what's outside directly. We can only build models and follow the math. Still, there are hints. Some researchers think that the strange behavior of dark energy might point to a connection with something beyond. Maybe it's a pressure from the outside, or an effect of the boundary between universes. Do CMB anomalies reveal the shape of a black hole universe? Most of the CMB matches what we'd expect from a flat, infinite universe born in a Big Bang. But some features don't quite fit. One of the most famous is called the cold spot, a region in the southern hemisphere of the sky that's noticeably cooler than the surrounding area. There are also alignments of large-scale patterns that don't seem random. Some parts of the CMB appear to line up in ways that shouldn't happen if the universe is completely isotropic. That is, the same in every direction. At first, scientists thought these might be glitches. Maybe they came from leftover noise in the detectors, or dust in our own galaxy getting in the way. But the anomalies have held up under scrutiny. While they're not strong enough to prove anything on their own, they continue to raise questions. Could they be telling us something deeper about the shape of the entire universe? If our universe came from a curved black hole interior, the shape of space might leave marks on the CMB. The anomalies might be echoes of the shape we're living in. In a flat universe, light travels in straight lines forever. But in a curved universe, especially one with strong internal gravity, like the inside of a black hole, light paths can bend, twist, or even wrap around. This could create unusual temperature patterns in the CMB. For example, if space is shaped like a three-dimensional sphere or torus, a photon traveling in one direction might eventually return from the opposite side. That could cause repeating patterns in the sky. Other shapes could produce different kinds of fingerprints. A universe with negative curvature, like a saddle, would make the CMB fluctuations larger on the largest scales. A positively curved space, like a hypersphere, could suppress those large-scale variations. Interestingly, some of the anomalies in the CMB look like suppressed power on the largest angular scales. That might hint at a closed, finite universe, something you might expect inside a black hole. The cold spot itself is still one of the biggest mysteries. It stretches about 5 degrees across the sky and is unusually cold compared to nearby regions. One explanation is that it was caused by a supervoid, a large empty region of space that photons passed through on their way to us. As they crossed the void, they would lose energy, arriving cooler than expected. But there's debate over whether the known voids in that direction are big enough to explain the effect. If not, then maybe the cold spot is a deeper clue of how space is curved in that region, or a leftover imprint from the very birth of our universe. Another strange feature is the so-called axis of evil. This name was jokingly given to a pattern found in the CMB where certain large-scale fluctuations seem to align along a single direction in the sky. In a truly random uniform universe, such alignments shouldn't happen, but they do, and they've been confirmed by multiple satellites. Some cosmologists think this could be a statistical fluke. Others wonder if it points to something more serious, a sign that the universe has a preferred direction or that its geometry isn't as simple as we thought. If our universe came from a rotating black hole, one with angular momentum, then the spin could leave a trace in the structure of space-time. That trace might still be visible today as a preferred axis, an imprint of the black hole's original rotation. The large-scale alignment in the CMB might be that imprint, a leftover mark from the moment our universe was born. Even more subtle clues might be hidden in the polarization of the CMB. This is the way the light waves are oriented, and it can carry information about the motion of matter and the shape of space in the early universe. The Planck satellite and others have mapped polarization with great care, and while the data is complicated, some patterns do suggest twists and turns that don't match simple models. These too might point toward a universe with a more complex internal structure. Perhaps one born from a space that was already curved or spinning. There's also the question of boundaries. If our universe is finite, does it have an edge? The standard answer is no. It could be finite, but unbounded, like the surface of a sphere. But if we're inside a black hole, then maybe there is a kind of boundary, a limit built into the shape of space. That could cause light paths to stretch in unusual ways, and it might even change the way fluctuations in the early universe were smoothed out. Some physicists have suggested that a black hole universe might produce a kind of lensing effect on the CMB, bending light in ways that create ring-like patterns or distortions. These would be extremely subtle and hard to spot among the noise, but future telescopes might be able to pick them up. Experiments like CMB-S4, the Simons Observatory, and even more advanced space missions are being designed to scan the CMB in finer detail than ever before. If the shape of our universe is curved in a hidden way, those missions might reveal it. The CMB is rich with information, but also with noise, and teasing out the true signals is incredibly hard. But every new observation adds another piece to the puzzle, and the anomalies continue to challenge our assumptions. If we really are living inside a black hole, then the signs may already be written across the sky in the oldest light we can see. All we have to do is learn how to read them. Would the laws of physics be different in a black hole universe? Physics depends on a few key numbers: the speed of light, the strength of gravity, the charge of the electron, the mass of the proton, and so on. These aren't explained by theory. We measure them, but we don't know why they are what they are. If they were even slightly different, stars might not form, atoms might not hold together, or life as we know it might never appear. These constants seem finely tuned, and yet we don't know where they come from. So if black holes are making universes, each one might roll the dice again on those constants. Some might be similar to ours, others might be completely alien. One universe might have stronger gravity, so stars form faster and burn out quickly. Another might have weaker forces, so matter barely clumps together at all. Some universes might not have stable atoms. Others might not allow for any structure larger than dust. Most would probably be stillborn, dead and empty almost as soon as they begin. But some might survive. Some might find a balance that lets complexity grow, maybe even life. This cosmological natural selection begets a population of universes dominated by those whose laws favor black hole formation. Not because black holes are special, but because they are reproductive. They pass on their traits, even if slightly mutated. If this is true, the laws of physics aren't fixed across reality. They apply within one universe, shaped by the conditions of its birth. Outside our universe, the laws might be totally different. The constants could have new values. The particles could behave in new ways. Even space and time could follow unfamiliar patterns. Are there meta-laws, rules that decide what kinds of physics are possible? Or is anything allowed, as long as the universe can survive long enough to evolve? Is there a boundary to how strange the laws can get, or do they range across an infinite spectrum of possibilities? String theory doesn't just allow one set of laws, it allows a vast landscape of them. Different ways of folding the extra dimensions in the theory lead to different physics. Thousands, maybe even more than 10 to the power of 500 different versions. Each one is a possible universe with its own rules. If black holes can explore this space, then each one might select a different fold, giving rise to a universe with its own unique shape. Are there signs that our universe was shaped by conditions that go beyond what we can observe? Even small clues might matter. Some scientists study whether physical constants have changed over time, even slightly. So far, the data suggests they're stable, but if any drift is ever found, it could hint at deeper layers of reality. Others study black holes themselves, trying to understand whether the information they contain, the mass, spin, and charge, could act like genetic material, shaping the universes they create. If each black hole creates its own rulebook, then our universe isn't just a bubble. It's a unique outcome of cosmic trial and error, a place where certain balances happen to emerge. Where light moves at a certain speed, gravity has a certain pull, and matter arranges itself in just the right way for stars to shine and planets to form. Whether this was luck, necessity, or the result of billions of previous universes trying out different combinations, we don't know. Entropy and time in a black hole universe. In our everyday world, time feels like it flows in just one direction. We age, memories form, stars burn out, and eggs don't unscramble. This steady march is something we don't usually question, but behind this feeling of time is a deeper pattern: entropy. it's a measure of disorder or randomness, and in almost every physical process, entropy increases. It's this increase that gives time its arrow. Without it, time might not feel like anything at all. In a universe born from a black hole, does the arrow of time still work the same way? Or could it do something different? Maybe even flow backward, stop, or split into more than one direction? To explore that, we need to look more closely at how time and entropy are connected. In thermodynamics, a low entropy state is highly ordered, like a new deck of cards in perfect sequence. A high entropy state is messy and disordered, like a shuffled deck. If you leave things alone, they tend to go from order to disorder. A hot cup of tea cools, not the other way around. A broken plate doesn't reassemble. These are the rules set by the second law of thermodynamics. But the laws of physics at the microscopic level, the rules that govern atoms and particles, don't care about direction. If you filmed a single atom bouncing around and played the video backward, it would still make sense. The basic equations work the same way in either direction. The only thing that gives time a clear direction is entropy increasing. So where did the direction of time come from? Why does our universe move from past to future, and not the other way around? One answer is that it started in a low entropy state. The Big Bang wasn't just the beginning of space and time. It was also the most ordered state the universe has ever known. Since then, entropy has been rising. But if a black hole formed our universe, then the question changes. What was the entropy like at the moment that universe began? Was it low like our Big Bang? Was it high? Or was it something else entirely? Inside a black hole, the deeper you go, the more time seems to slow down from an outside perspective. Near the singularity, time and space might swap roles. The future might point toward the center. If a new universe forms beyond that center, maybe it starts with its own new time, flowing outward from the singularity. This newborn universe might not follow the same thermodynamic path. If it began from a bounce, the entropy conditions might be totally different. Some theories suggest entropy could decrease on the other side, meaning time might seem to flow backward from our point of view. Others suggest entropy might start low again, but only locally. Maybe different regions have different arrows of time. Maybe they even meet. This leads to the idea of time symmetry. What if the universe born from a black hole is a time mirror of the one that created it? Our universe expands forward in time. The other might expand in reverse. From our perspective, that reverse time universe might look like it's collapsing. But from within, its inhabitants would experience their own time flowing normally, just like we do. It's even possible that both directions of time emerge from the same moment, like a tree branching in both directions from a seed. One side becomes our universe, the other becomes a universe with reversed time. To observers in each, time feels normal, but from a broader perspective, it's a mirror-like structure with two time arrows pointing away from a shared origin. Other possibilities are even stranger. What if time inside a black hole-created universe isn't one way? Could it loop? Could it fork like paths in a maze? Could some regions have time that runs forward, while others drift in different directions, or remain timeless altogether? In certain models of quantum gravity, time might emerge only at large scales, as an average behavior, not a built-in part of reality. In such models, the idea of a single arrow of time might be too simple. In a black hole-created universe, especially one with wildly different physics, time might be flexible, even fragile. It might not follow a single rule. There are even hints from black hole thermodynamics itself. Hawking radiation is random, spreading disorder, but the black hole also hides its interior from the outside. So where does the information go? If a universe forms inside, maybe that's where the order is preserved. Maybe the black hole balances the entropy increase outside with something new growing inside, a kind of entropic trade-off across realities. If a black hole creates a daughter universe, what sets the arrow of time in that baby? Is it inherited from the parent, or does it arise independently? Some theorists believe the moment of birth defines the arrow. From that moment on, entropy grows and time moves forward. But if two baby universes are born in opposite directions, they might each experience time differently, yet remain part of the same overall reality. Maybe what we call now isn't a universal slice of time that stretches everywhere. Maybe it's something that only makes sense within a given region. In one universe, time moves forward. In another, it might be frozen, reversed, or split. The observer and the structure of the surrounding space-time helps decide how time behaves. In the far future, even our own universe could face strange changes in its time behavior. As expansion continues and entropy grows toward its maximum, time might lose its meaning. In a heat-death scenario, when everything is evenly spread and no more work can be done, there might be no reason for time to move at all. The arrow would vanish. But if that death results in a new black hole, and that black hole spawns a new universe, then time might start again, with a new direction, a new entropy path, and a new story. What happens when a parent black hole evaporates? We know from Stephen Hawking's groundbreaking work that black holes don't last forever. They slowly leak energy through Hawking radiation, shrinking over unimaginable timescales until they disappear completely. If our cosmos depends on a parent black hole, does its end mean our end too? Or does our universe keep going, cut free from its parent? From the perspective of the parent universe, the black hole shrinks slowly, radiating away mass until it's gone. But inside, things look very different. To someone inside the black hole's universe, time doesn't necessarily line up with the time outside. Relativity tells us that time can flow very differently depending on your position in a strong gravitational field. Near an event horizon, time for an outside observer moves faster and faster compared to the time for someone falling in. This means that even if the black hole evaporates quickly from the outside, the universe inside could experience billions of years, or perhaps an infinite stretch of time, before anything changes. Some models suggest that once a new universe has formed beyond the black hole's singularity or bounce point, it becomes a self-contained space-time. That universe expands on its own, developing its own timeline, completely cut off from the fate of the parent universe. In this view, the black hole in the parent universe is just the gateway. Once crossed, what happens to the door doesn't matter. The new universe carries on whether the parent black hole evaporates or not. But other possibilities can't be ruled out. What if the connection to the parent universe remains active? What if the evaporation of the black hole also drains energy or information from the universe inside? Could the shrinking of the black hole's event horizon squeeze the internal universe, slowing it down or even tearing it apart? We don't have the physics to answer that with certainty. There are scenarios where the evaporation of the black hole happens so slowly, across timescales longer than trillions of times the age of our universe, that from the inside, the universe has more than enough time to develop, evolve, and possibly even end on its own before the black hole fully evaporates. In that case, the lifespan of the black hole wouldn't matter practically to the beings inside. Yet if there is a deep link between the two, it might mean that black hole evaporation is a two-way process. If the black hole evaporates and information about what went into it escapes with the radiation, where does that leave the universe that formed inside? Does its existence get unwound as the black hole's information leaks out? Or does the process of preserving information only apply to the parent universe's side, leaving the child universe untouched? If space-time inside the black hole becomes its own expanding bubble, then it might detach from the parent universe completely. Some theories even suggest that once the bounce happens, the new universe inflates so quickly that it severs any causal connection to the parent. In that case, even if the parent black hole evaporates, it's as if the child universe has already flown beyond reach, like a ship leaving a harbor and never looking back. Some speculative models propose that when a black hole reaches the final stages of evaporation, a violent release of energy might occur, an explosion on cosmic scales. Could that burst cause changes inside the universe seeded by the black hole? Could it inject energy, causing dramatic shifts in the internal universe's physics? Or maybe the evaporation is smooth from our point of view, but corresponds to a sudden event in the child universe. If the black hole erases information as it evaporates, this would violate one of the bedrock rules of quantum theory. But if the child universe carries that information forward, then evaporation might not destroy it at all. Instead, it just relocates it into the growing universe on the other side. This would mean the child universe becomes the true record of what fell into the black hole, even after the black hole is gone from the parent universe. In the end, the evaporation of the parent black hole could mean many things. Our universe could keep expanding, fully self-contained and unaffected, or it could still depend on the existence of the black hole in ways we don't yet understand. Maybe it's only our limited knowledge of quantum gravity that keeps us from seeing the true picture. Whatever the case, these possibilities show just how far the questions of black holes reach. They don't just challenge what we know about stars or gravity, they touch on the fate of everything. Could advanced civilizations learn to harness the interior? Black holes are usually seen as the end of the line, but to a civilization far beyond our level, something millions or billions of years more advanced, a black hole might look like an opportunity, a machine waiting to be understood. If the inside of a black hole is a vast space, then the idea of harnessing it becomes a question of engineering, of knowledge, of control. What could a civilization that's cracked the secrets of space-time do with that kind of environment? First, there's time. Near a black hole, time behaves in strange ways. Imagine a civilization that doesn't just understand this effect but can use it. For them, the edge of a black hole could become a place to hide from time. They could store information or objects in deep orbits where they age more slowly. They could send a signal into a black hole and have it pop out millions of years later from the point of view of the outside universe. Or the opposite. They could wait near the edge of a black hole and watch as whole galaxies age and vanish while only minutes pass for them. In a way, this would be a kind of time travel, not jumping forward or backward exactly, but shifting perspective, choosing how fast or slow to experience reality. What about the interior? If the inside of a black hole really is another universe, or at least a vast space beyond the reach of normal reality, then a civilization might try to enter it on purpose. Not as a doomed explorer, but as someone with a purpose. The interior could be used to run simulations. If the space inside a black hole is cut off from the outside, it becomes the perfect sealed system. No interference, no leaks. All the energy and matter that went in is still there, transformed, trapped. To a superintelligent species, this could be like a giant cosmic hard drive. They could encode data in the matter that collapses, use it to set the starting conditions for a universe-sized simulation. Maybe they wouldn't run just one. Maybe each black hole becomes a new test bed for evolution, physics, or consciousness. They could create entire worlds inside and then watch from outside, or even enter those worlds to experience them directly. Of course, entering a black hole is dangerous for any normal being. But for something not bound by flesh or bone, something that exists as pure information, or something that can control its own structure at the atomic level, those dangers might be manageable. They might be able to cross the event horizon without harm. Or they might not enter physically at all, but instead send probes or signals designed to survive the transition. Black holes are filled with potential energy, not just because of the matter they contain, but because of how they warp space-time. An advanced civilization could use spinning black holes to extract energy, a method already theorized by physicists. But if they go a step further, they might be able to access energy from the inside, not just the outside. The interior universe might have its own stars, its own structure, its own thermodynamic flow. In a way, the black hole could become a kind of battery that contains an entire cosmos worth of energy. Learning to tap into that safely would be a sign of truly cosmic intelligence. Could life, or something like life, exist inside a black hole? Maybe not in the form we know, but in some adapted or artificial way. A civilization that sees our universe as too chaotic or too exposed might build habitats inside black holes. Sealed, secure, shielded from external threats. These would be more than bunkers. They'd be full environments, protected by the event horizon, governed by custom-designed physics if the interior can be manipulated. If such beings could choose how a black hole collapses, they might even program the resulting universe to suit their needs, tuning the constants of nature like settings on a machine. If black holes can create new universes, then this could be the ultimate form of technological creation. Not just a computer, not just a machine, but a whole cosmos, tailored from the ground up. A civilization might reach a point where it no longer just explores space, but makes it. Each black hole becomes an experiment in cosmic design. Some might be abandoned, others might be seeded with particles, stars, or even early forms of life. If intelligence can survive the transition, it could enter these new realms and grow again, spreading across layer after layer of nested universes. And if they are doing this, we wouldn't know. From our side, a black hole looks simple. A few numbers, mass, spin, charge. That's all we can detect. But on the inside, everything could be different. A civilization could be thriving just beyond the horizon. They could have filled black holes with entire societies, entire histories, and we would still look up at the night sky and see only dark, empty spots. If such a thing is possible, would we ever be able to do it? Our species is still struggling to understand black holes from a distance. We can't send anything inside. We can't even detect Hawking radiation yet. But if the idea is true, then perhaps one day we could too. It might take thousands or millions of years. But maybe the future of intelligence doesn't lie among the stars, but beneath the surface of the most dangerous objects in the universe. But this is where we end our own exploration. Were there any wacky ideas that we missed? What would you like us to cover next? Send us your ideas in the comments, and if you enjoyed the video, consider leaving a like and subscribing. Thanks for watching.